This MedChem meeting at Cambridge is now one of the top MedChem meetings in the world, and as such, we have liberty to try one or two new things at each meeting. This time, we're looking at doing a live webcast of a session, and that session is going to be the one now on neglected and tropical diseases. We decided to do this for two reasons. One is that we felt that it gave an opportunity to put focus on neglected diseases and allow people to see what scientific opportunities are there, but also perhaps to cast a spotlight on some of the really fantastic science that's being done in the area and expose it to a wider audience. The meeting is going to have several presentations, but also we're going to very kindly got Kelly Chibala and Charlie Mowbray to do, in Kelly's case, a short introduction to just give a bit of focus to the area, and Charlie Mowbray to wind it up at the end, but also perhaps to highlight some of the opportunities that are available. Our first speaker is Kelly Chibala. He got his PhD in organic chemistry at the University of Cambridge, and then followed several postdoctoral stints at University of Liverpool, Scripps Institute. He was Sandler Sabbatical Fellow at University of California, San Francisco, Fulbright Fellow at University of Pennsylvania School of Medicine, and also a visiting professor at Pfizer in the UK. He's now a full professor of organic chemistry at the University of Cape Town. He is also a member of the UCT Institute of Infectious Diseases and Molecular Medicine. And today he's going to talk to us, give us a brief introduction, and then talk about PI4K inhibitors that target multiple life cycle stages for human malaria parasite. Thank you.
Chris, thank you. Thank you for that very kind introduction. And many thanks to the organizers, I think, for giving us, not just me, this opportunity to speak to you, but also to really give us this opportunity to showcase what's happening in the neglected tropical diseases space. So it's really appreciated. But I think I would like to reserve my special thanks to Andy Williams. Andy Williams, I think it was our meeting at Eli Lilly last year that eventually led to this. So a special thank you to you, Andy, for this. All right, so as Chris mentioned, we'll come back after 10 minutes to talk about my actual projects. But what I will do now is to just give you an overview of the field of neglected tropical diseases. And I have chosen what you see here is in fact the kind of diseases my colleagues will eventually speak about in terms of their projects. And then I'll finish off with just discussing with you some of the challenges in this field from a drug discovery perspective that really puts really a wise perspective on drug discovery, especially for this field. All right, so what are neglected tropical diseases? This is the summary of these. So this is a total of about 17 diseases. I'm not going to go through all of them, but it gives you an idea of what we're dealing with here. In fact, subsequent to me preparing this slide, I became aware of an additional 3 which have been added to this list. So we have, as of now, 20 neglected diseases. Now, of course, you might be wondering, why is malaria and TB missing? Because they're supposed to be neglected. Well, the malaria and the TB people don't feel so neglected. These are the neglected of the neglected, and that's why. But the highlight here is on Leishmaniasis, because it's a topic that somebody will speak about in the session. So what I will proceed to do now is to, before I go on to this, is first of all, again, to emphasize, these are diseases that primarily affect populations in the developing world. So it's not something you will find ordinarily in Europe or North America, although some of them, like Chagas disease and Leishmaniasis, I think are finding their way in parts of North America and Europe to some extent. But the major brunt of the infections are borne by people in the developing world. What about the burden of this? And I've just chosen to highlight this figure is based on a 2007 publication looking at the 10 leading causes of life years lost to disability and premature death. And you can see the impact of the NTDs collectively in terms of being in the top 10 of the leading causes of life years lost due to disability and premature death. So this is the combination of the diseases you saw on the previous slide, and then there is malaria, and there is TB, which will be in this session. Again, a significant burden if you consider the level of investment that hasn't gone into these areas. All right, what is the reality of product development in this space? Of course, one has to acknowledge, first of all, that over the last 5-10 years, there's been tremendous progress in terms of the work that's gone into drug discovery for these diseases, exemplified by product development partnerships, PDPs, like Medicine for Malaria Venture, the Global Alliance for TB Drug Development out of New York, and also, of course, the drugs for neglected diseases. We've seen progress over the last 5 or 10 years. But there still remains very significant imbalances in terms of the products that are getting their way through to clinical development in this space. I think this is really self-explanatory. If you consider this pie chart here, and this is a survey of products were developed between the year 2000 and 2011. And you will see some of the stats summarized here, that only about 4% of new products were really developed for NTDs. And these were specifically just different formulations and combinations of existing drugs, so not new chemical entities. The other statistic, if you look at the new chemical entities you see here, only about 1.2% of new chemical entities introduced during this period were really from NTDs. And the picture goes from bad to worse. If you consider the number of clinical trials that are happening globally, and only about 1.4% of clinical trials of the nearly 150,000 clinical trials happening globally actually happen in the NTD space. Again, a very serious situation. And of course, the funding, if you consider the level of investment in the other diseases compared to NTDs, this is only about 1% of global investment that goes into drug discovery and development for this. So we're dealing with what we're calling a fatal imbalance between the investment levels and the level of activity in discovering new drugs for NTDs. All right, so what I'll run through now in the last few minutes or so, I've only probably prepared just a couple of slides to give you an overview of what each disease is about. And these are diseases which my colleagues will speak about in a bit more detail in the context of their specific projects. So what is Leishmaniasis? This is actually a disease that's actually transmitted by this vector, which is the sandfly. It really affects a lot of people. This map, I think, is a good illustration of the kinds of areas where you find this disease. And I mentioned earlier at the beginning, some of these, even though they are really diseases which impact the developing world, you see Leishmaniasis really present also in this part of the world as well. There are two types of Leishmaniasis, and I will show you on the next slide what you can see from patients that suffer from these diseases, which are debilitating. One type is what we call the visceral Leishmaniasis, which, if untreated, is fatal. The second one is what we call the cutaneous Leishmaniasis, which is often manifested with skin lesions and deformities, as you will see on the next slide. These are the typical symptoms of the disease: fever, enlarged spleen and the liver, etc., etc. And if you just look at the impact of this disease on people, so this is a photograph of a patient suffering from the visceral Leishmaniasis here. And as I mentioned in the previous slide, this is fatal if it remains untreated. And there are about 400,000 cases of visceral Leishmaniasis every year. On your right are examples of patients suffering from the cutaneous forms, which is expressed either as a localized cutaneous Leishmaniasis or of diffuse cutameniasis here. And the much more deforming form of the disease is what we call the mucocutaneous, and you can see the impact on people. What we've seen, of course, and you will see this in my concluding slide, is that over and above these infections I've described here, we now have additional challenges and complications arising from the rise of other infectious diseases in the same regions of the world. And so the additional challenges with Leishmaniasis, of course, are co-infections, for example, with HIV. Again, complicating the picture in this area of NTDs. So that's enough about Leishmaniasis. Again, just to give you an overview of what causes it and how it's transmitted and the different forms of the disease. The second one, again, just a couple of slides, is malaria. So malaria is another one of these very significant diseases in the developing world, caused by about 5 species of the parasite responsible for the human disease. The most fatal of the disease is caused by the falciparum species, but also vivax, which is also responsible for relapses in malaria. The vector is a female Anopheles mosquito. It's a she, not a he, that transmits the parasites during a blood meal. And the typical symptoms include chills, fevers, vomiting, anemia, and malaria is a very, very fast killer if there's no access to medications. And if you look at some of the statistics summarized here, there's at least 3.2 billion people at risk from malaria. And of course, unfortunately, the major victims of this disease, more than 2/3 of the victims of the disease are children under the age of 5. Again, a very, very significant issue. There's been tremendous progress over the last 5-10 years in terms of the impact of new drugs and other interventions. However, still, malaria still remains a very significant problem here with at least more than 200 million cases of malaria every year and at least more than 400,000 deaths from malaria. Still unacceptable, but of course significant progress if you compare to just 10 years ago. I'll come back to this malaria in my talk in a bit more detail. The last one is tuberculosis. So TB is a complex disease caused primarily by Mycobacterium tuberculosis. And the mode of infection is typically through aerosol droplets. So this is not something that is constrained or restricted to the developing world because we're all traveling constantly. So this is a serious infection, not just for the developing world, but for the entire global community. From a drug discovery perspective, what makes TB even more challenging in terms of new drugs for TB is not only are we battling with a heterogeneous population of bacteria, we have the so-called persisters, and then we have the non-replicating forms that are dormant. In fact, 1/3 of the world's population carry the TB bacteria, but it's latent TB, and of course only become activated due to a number of risk factors. The other one is that we're only dealing with the metabolically active disease. But in addition to the heterogeneous population of bacteria, we also have the bacteria in multiple environments, from the macrophage all the way through to the bone and the caseum. And the challenge of TB, as you will see on the next slide, the duration of treatment is so long, mostly because most drugs are not able to penetrate some of these compartments where the bacteria resides, especially the caseum, for example. But the primary site of infection of TB are the alveolar cells of the lung. What about some statistics for TB? Again, a very, very serious global problem. About 5,000 deaths from TB daily, at least. It's a huge, huge, significant number. As I mentioned on the previous slide, the duration of treatment for TB is extremely long. To treat drug-sensitive TB takes a minimum of 6 months. And to treat the resistant forms of the disease can go up to anything more than 2 years. Again, that in itself presents multiple challenges, including compliance issues when it comes to drugs. And also, as you see, again, in a bit more detail on the next slide, is that the success of treatment goes down as you go from the drug-sensitive TB to the resistant ones. And of course, this remains huge, huge, serious unmet medical need. And of course, when it comes to children, about 1 million children are affected by this disease. This is what I just mentioned on the previous slide. So as you go from treating drug-sensitive TB here to drug-resistant TB. So this is the multi-drug-resistant TB. This is the extremely drug-resistant TB. And there's a third category which I've not included here, which is the totally drug-resistant TB that doesn't respond to any of the drug regimens which are available presently. So again, you will see that the therapies to treat TB are extremely urgent, not just looking at shortening the treatment duration, but also dealing with these very serious cases of drug resistance with varying degrees of complexity across different populations. All right, let me finish off this part of my talk and just try and very, very briefly and quickly discuss some of the challenges, particularly for drug hunters when we start all these programs, thinking about the target product profile of the patient that we have in mind, living in very, very poor communities across the globe, is obviously we're dealing with people who live in very, very difficult environments. And I mean difficult environments, not just from a perspective of infrastructure, but also some of these environments also are very difficult from a political perspective. The second thing that you're dealing with patients who are actually very poorly malnourished. And of course, that has implications on how medicines perform in that patient population. And of course, as I mentioned when I was talking about Leishmaniasis, the same patients are also subject to infection by other multiple organisms. And so this co-infection also creates another level of complexity when we're dealing with treating these NTDs. And as I mentioned earlier, these are people ideally, primarily who are very poor, live in very poor communities in very, very difficult conditions across the globe that you're dealing with here. We talk about dosing regimen. You make a number of assumptions about the patient that you have in mind. But often, if you go to a remote part of some countries in Africa, for example, just to get from one village to the next village really has its own challenges. That often people cannot even comply with that particular dosing regimen. So things we take for granted, we can just go to a hospital, are not necessarily guaranteed in many parts of the world because of the nature of these conditions. Most people either have limited access to infrastructure, health infrastructure, medical staff, but many of them don't even have access to that infrastructure or medical staff. So when you think about coming up with a drug for these populations, it's not just the cost of goods that we think about, and the cost of goods issue becomes even more significant for these NTDs because of the people that we're dealing with as patient populations. And things that we take for granted, there are no hospitals, there is no power, there's no electricity, there are no fridges. And so when you think about delivering your innovation to patients in these communities, these are some of the things that you really have to think about. It creates an extra level of complexity. So I hope that in the last 10 or so minutes I've given you a little flavor of the challenges with NTDs. And again, really, really grateful to Andy and the organizing committee for really trying to bring some focus to this very important area of research. I'm going to switch now to my actual presentation. All right, so from the very beginning, just to acknowledge that this is a project that we conducted in collaboration with the Medicine for Malaria venture out in Geneva. So I'm representing a global effort working on this program. But what I would also like to do is to take this opportunity just to introduce to you our Drug Discovery Center, H3D. You can see this is at the tip of Africa because I'm from Cape Town. And you notice we actually rebranded last year. This logo is very significant. It's not just that when you look at the logo, you will see, obviously, it's Africa, assuming that you've done some geography. But it's also the color. This is the color of the African soil. It represents warmth. Anything blue means that you come from a country where there is snow, and there is no snow in Africa. So this is our Drug Discovery Center. This was founded back in 2010. If you didn't know, 2010 is a very significant year in the history of humanity because 2010 is the year when Africa hosted the Soccer World Cup. England lost in the semis, that World Cup. But it's very significant because, but also that's when the center was established, officially launched in April of 2011. This is University of Cape Town Drug Discovery Center, located across 2 sites on campus. We have the chemistry group up on upper campus of the university, and I have a picture to show you at the end of my talk. The second group is a biology group, which is sitting at the medical school in this building here. So this is the Institute of Infectious Disease and Molecular Medicine. So this is actually on the medical campus where we have biology and screening efforts happening there. And then we have a third component of H3D sitting at the hospital. This is the Grootskia Hospital. This is a very, very significant national heritage because it's in this hospital that Christian Barnard performed the first world heart transplant. This was in this building here. And H3D is embedded within the clinical pharmacology on one of the floors of this hospital. So this is an integrated platform, chemistry, biology, pharmacology, and DMPK. It's a first and only one of its kind on the continent. We've grown people from, used to have 5 postdocs back in 2011 to about 60 people as we speak now. What we have in place, these are capabilities. We have MedChem, we have CAD as well, and of course biology to support drug discovery programs in malaria, TB, and other pharmacology assays that we have in place. And then we have a suite of DMPK assays in vitro, as well as the in vivo rodent pharmacokinetic capability also available in our unit. And much more recently, we've managed to successfully, actually last year, set up and validate and roll out this humanized mouse model of P-falciparum to allow us to study the human infection in rodents. So that's enough about H3D. Let me now switch to this particular project. So when we think about malaria drug discovery, first of all, just to remind you of the infection and what is the life cycle of the malaria parasite. So everything starts here. And so this is a female Anopheles mosquito. During a blood meal, then releases these parasites we call sporozoids, which enter the bloodstream and eventually migrate to the liver. So the liver is the first port of call for the parasites. There are no symptoms at the liver stage of the infection. It's when the parasites in the liver then begin to multiply and then begin to invade the red blood cells. So all the clinical symptoms of the disease are really, really felt or experienced when the parasites infect the red blood cells. But what happens also is, in addition to the liver stage parasites that then eventually migrate into the blood or the red blood cells, is there are also other forms of parasites especially in the Plasmodium vivax species of the parasite, which we call hypnozoids. So these are basically dormant forms of the parasite that then at some point could be responsible for relapse. This is the process that happens within a period of 48 hours. And the parasite undergoes asexual development. And of course, if we don't treat malaria at this stage, it's extremely fatal. People die very, very quickly. The final phase of the life cycle within the host is the asexual parasites. These are so-called gametocytes. And these are the transmissible forms of the parasites, which the mosquito, during the next blood meal, feeds on. And this is actually how then malaria is transmitted from person to person. So these gametocytes are then taken up by the mosquito, and then of course they undergo additional development within the mosquito, which are then passed on during the next blood meal of the parasite. So from a drug discovery perspective, the focus in the community from the perspective of contributing to malaria eradication or elimination from a chemotherapy perspective is to identify molecules which impact at least 2 of the life cycle stages, preferably molecules that kill the parasite at all multiple stages of the parasite. So this is actually one of the important target candidate profiles that we're looking for, setting up screening cascades and assays which allow us to interrogate the parasite life cycle. And I focus on series that give us benefits of killing the parasite at all the life cycle stages. So that's what you will see in our project. All right, this is the history of the project. This was a commercial biofocus, soft focus library. So these are libraries which are typically designed with a particular gene family in mind. This library was screened in Brisbane by Vic Avery on the sensitive strain of the parasite, but also on the resistant strain of the parasite. But also, in parallel, this library was also screened for cytotoxicity, so that we then focused on prioritizing series which showed at least 80% inhibition of parasite growth at that concentration, and a reasonable selectivity index in terms of selectively killing the parasite without harming normal cells. I'm not going to describe to you everything we've done. Most of this stuff is published, but I will focus on the work we've done on this so-called SFK40, soft focus kinase 40 sublibrary, which is a library of aminopyridines. The project goal, again, to remind you from the beginning, first of all, this is about an oral drug. This is a very important target product profile because the patient is in a very poor, remote area of the globe. So it has been an oral drug for P. falciparum malaria, but also potentially vivax malaria, which again, as I said earlier, this is the parasite infection that leads to relapse in malaria as well. So a very important problem. The second goal is to ensure that any new chemical entity is not cross-resistant to existing drugs. And finally, consistent with the mandate of trying to contribute to malaria elimination and or eradication, is that we also want compounds that work not just at the blood stage, but also are able to kill the parasite in the liver, but also kill the transmissible forms of the parasite, or the gametocytes, so that we can potentially contribute to blocking transmission of the infection. So this is a screening cascade that was put in place to help us fulfill this project goal. All right, what I'm not doing in this lecture is tell you the story that led to the discovery of this compound here. This compound, the full story was published this year. This compound is now gone to phase 2 human trials this year. It came out of this program, which I'm going to describe. But I will focus on actually describing to you the backup strategy in terms of identifying the next generation of PI4K inhibitors, And I will share with you, in summary, what we did to identify the target as well. But you can read the full story of this compound in this paper published this year. At the time of initiating the backup program, the only differentiating criteria for us was solubility. And I think working with the clinicians doing the phase 1 trial, it was quite evident that solubility was an issue, confirmed in the phase 1 in terms of having variable exposure of the drug across different volunteers. So at the time of initiating our backup program, solubility was the only criteria we focused on in terms of developing the next generation of compounds. So this is a summary of the initial hit from the high-throughput screening. And there are basically 4 different diversity points that we focused on. So this is divided between the core aminopyridine, the 3 aryl substituent, and the 5 aryl substituent here. So this is the aminopyridine initially, and most of this work has been published in terms of the initial essay that we did on this. And I'm just giving you some of the examples of what we did here. But let me switch just to give you a sense of the kinds of things that we did to drive the SAR forward. With respect to the 3 aryl substituent here, in general, things that were tolerated here tended to be aromatic rings with electron donating groups and electron withdrawing groups. Again, so there was quite a diverse range of substituents that we could introduce at that position. And more specifically, in terms of improving potency, substituents with a pyridyl group were really, really important in improving the activity of the compounds. Whenever we introduced this kind of substituents at the 3 position, there was either a drop in potency or complete abolition of potency of the compounds. The second SAR exploration focused on this 5 aryl substituent here. And again, the general finding from more than 400 analogs we prepared here was that the optimal substitution was a para-aromatic substituent with an electron withdrawing, polar electron withdrawing group in the para position of the aromatic ring. Anything else that we did, electron withdrawing, non-polar, as well as this kind of substituent here, either gave us a drop in potency or completely lost potency. But the key change for us in terms of addressing the solubility liability that we knew we had in the compound that went to the clinic was actually changes to the core structure here. Sorry, I need to find another. Right. So this was a major transformation for us because immediately we noticed that actually changes to the core structure really gave us improvement in potency, but also in some analogs also gave us some improvement in solubility. Not quite optimal, but I think it was a clear direction for us to pursue these pyrazines as opposed to pyridines. All right, let me cut the long story short. So these are just the front-runner molecules from the series. We had hundreds of them prepared. And what you see from this initial series of compounds here, all based on the pyrazine core, that in general, we had very good in vitro potency. That was retained and actually reproduced from the aminopyridines series as well. But we also saw that actually we could also achieve very good in vivo efficacy in the rodent Plasmodium berghei efficacy model. So this compound here and this compound here. So what's in brackets here is what we call the mean survival days. So anything up to 30 days is considered a cure. And what is a cure? When you take a blood sample from the mice and you check under a microscope to see whether there are any parasites. When there's a cure, we don't see any parasites after 30 days of experimentation. So we could see already that we were moving in the right direction in terms of not just the in vitro potency, but also the in vivo potency of the series. Of course, Herg was an issue that I think we had to keep an eye on as part of the process. But you can see, again, early on, solubility was really a major issue in most of these front-runner compounds here. That was an exception, but the vast majority of the compounds really suffered from either poor solubility or low solubility. All right, what do we do again? Again, we focused on, after having understood the SAR from the aminopyridines, we knew which position was very sensitive in terms of either abolishing potency or retaining potency or even improving potency. And we also understood where we could make changes to the structure to help us improve the physical properties. And that was actually this position here. So this 5-area of substitution here, especially specifically with polar electron withdrawing groups, was optimal. So this is really a focus on either amides or sulfones, much more specifically. And you will see from the analogs here that we see, in general, improvement in aqueous solubility while also retaining potency. And you can see the compounds of interest here, here, and here. So again, this was really giving us confidence that we're moving in the right direction. Okay, what was next? Of course, we focus on a few front-runner compounds. How do we then make sure that we can demonstrate the pharmacology proof of concept, that we really can see efficacy in the humanized mouse model? So this is the data here. What I showed you on the previous slide was in vivo efficacy data in the rodent mouse model. So this is the Plasmodium berghei mouse model. This data is in vivo efficacy in the Plasmodium falciparum humanized mouse model, which of course is relevant. It's a relevant human infection and help us when we're doing human dose predictions or PK/PD modeling. So what you see here, again, not to bore you with the details, you see, and this is really thanks to GSK as part of the network, you can see that the ED90 was less than a mg per kilogram for all these front-runner compounds here, which I'm representing here. And all the other PK parameters in general were also quite good, particularly for this compound here with very good oral bioavailability, and this compound here also with very good oral bioavailability. Again, very much consistent with an improvement in solubility, which obviously could also have been limiting absorption. We improve it, and we improve the PK parameters, including the bioavailability. All right, I'm back to this slide which I showed you at the beginning. So what we're looking for are compounds that are able to kill the parasite at multiple stages. So this is the data I'm going to show you in summary here. So these are the 3 front-runner compounds that we selected for extensive profiling to look at the effect on the different life cycle stages. So this piperazine compound here is in blue, and this amide here is in green, and of course you can see the color of that. And what you see, again, not to bore you with all the compounds here, but if you just focus on this compound here, you can see in the liver assays. So this is the liver stage parasite from the cynomolgus monkey. You can see this data is nanomolar, so very potent on the liver stage from cynomolgus, but also even much more potent on the rodent parasite, Plasmodium berghei liver stage, less than 1 nanomolar potency. Very good blood stage activity on the asexual blood stage parasites here as well. And we also looked at the stage specificity of the compounds during the asexual reproduction cycle of the blood stage infection. We also tested the compound on clinical isolates, and we see that this compound retains activity also on circulating clinical isolates. The other important data for the compound in blue that also has an effect on the transmissible forms of the parasites. And we subsequently did important experiments in the mouse model to see whether we could interrupt mouse-to-mouse transmission, so giving us a level of confidence that this compound could impact malaria eradication or elimination by blocking transmission of the parasites. So again, the message on this slide is that we really achieved a very important goal from the beginning of identifying compounds that impact the parasite at all the life cycle stages. I'm going to finish off in a couple of slides now with telling you about the target identification work. Most of it is actually described in the Science Translational Medicine paper, which I showed you earlier. But in summary, all we did was we took two complementary approaches. One was a genomics approach, where we applied drug pressure, raise resistant parasites, which are resistant to the drug, and then we do whole genome sequencing and look for where mutations occur. And so we saw single nucleotide polymorphs in the gene encoding for PI4K. We also did a complementary approach using chemoproteomics or kinobeads profiling, which really allows you to study the interactions between a small molecule and more than 300 human kinases. This technology has been adopted to a number of parasites, including the Leishmania parasite, but also the malaria parasites, with about 89 kinases that could be studied using this technology. So the bottom line is that this approach also, from the pull down and the binding experiments, again confirmed PI4K as the target, again supporting the data we got from the genomic approach. We also did the functional enzyme assay to look at whether we could see any correlation between inhibition of the enzyme and antiparasitic activity, host cell activity. And we saw also quite a very nice correlation between the enzyme inhibition and antiparasitic activity. All right, this is my final slide. Again, just to conclude, this was really the goal of the project was an oral drug which impacts the parasite at the different life cycle stages. So that goal was achieved. During the process, we made more than 300 compounds from this series, a number of them with very good in vitro potency, as well as in vivo efficacy, with very impressive less than 1 mg per kilogram ED90 values. Again, very much consistent with the safety pharmacology, which of course was always extensive, and toxicology in rats, which led to nomination of the compound called UCT943, which is actually this compound here. This compound is UCT943. UCT943, University of Cape Town 943, meaning that now we've decided to colonize MMV instead of using, so this was the MMV number, now this is a UCT943, so not MMV 943. All right, and this was approved as a preclinical development candidate last year. All right, this is many thanks to the team, international team. These are people from University of Cape Town and MMV. Many thanks to James Duffy, who's in the audience and also presenting a poster. He's been the MMV project director, and thank you, James, for the support. These are all our collaborators from GSK and other places as well. So the final slide, which I can't resist showing, is where I come from, which is this. And if I'm allowed to boast about one thing, please just bear with me. So this is the upper campus of the University of Cape Town. This is the famous Table Mountain here. And this is the Atlantic Ocean. And then the Indian Ocean is on the other side. This is a rugby field. South Africa, we play rugby. And we don't mess with anyone. So the chemistry team is in this building. It's an ugly building. But they say, don't judge a book by its cover. You have to go in, and then you find out. But let me now boast. I live here. Okay. And I'm in charge of this block here. And it takes me 5 minutes to get to my office. 7 minutes if there are too many students on campus. With that, I thank you for your patience and your time.
thank you, Kelly, for getting us off to a fabulous start. If there are any questions.
Hi. You didn't say much about selectivity against, in particular, other lipid kinases. Can you comment on that and whether it's an issue or not?
Yeah, so it wasn't an issue, and more specifically, there was no effect on the PI4K alpha and beta, the human PI4K alpha and beta. The only human kinase actually inhibited was a kinase called P1P4C2B or something. This target actually apparently, it's also an off target of Gleevec, the anti-cancer drug. But it was very, very clean in terms of just going after the parasite kinase. We had another series which was a bit more promiscuous, including going after PI3K and a number of lipid kinases. But this one was very clean, except that one human target which is the off target of Gleevec as well.
Thanks.
You mentioned that oral delivery was very important for because of the environment, etc. But wouldn't a once-monthly intramuscular injection be suitable in terms of patient compliance and ease of delivery, making sure that people actually get drug?
Yeah, so that's one approach. In fact, MMV and other people are trying to work on as well. But still, when you talk about the vast majority of people who live in very remote areas where there are no hospitals, I think it's much easier for them to take tablets than get an injection. So I think the population we're talking about here largely has no access to medical infrastructure and hospitals. Yeah.
Thanks, great talk. I wonder if you could comment a little bit on IP and how that might be different for your research programs, how much you worry about protecting the IP, as well as, is it more flexible that you think if, say, a big pharma partner owns a big area of patents and you think that there's interest for you there, is there more of an opportunity for you to get access to that space?
In this space, so we talk about IPR, intellectual property rights. In this space, it's intellectual property responsibility. So I think the driver behind securing IP, obviously it's not for commercial reasons, is to ensure that the medicine gets to the patient, so that at some point, when you have to look for a pharma partner, that there are no issues with IP, that you can pass on the program to a pharma partner. And in fact, this has happened in some of the programs. So I think it's more to ensure that MMV, for example, is not obstructed from delivering the product to the patients.
Thanks.
Okay, in the interest of keeping on time with the webcast, I think we'll move on now. And if you just join me in thanking Kelly once again. Our next speaker is Christoph Boss. He did his undergraduate and PhD at the University of Bern, and then did a postdoc at the Scripps Institute. He then moved back to Switzerland to Process Research Group in Specialty Custom Chemicals, and then moved to Actelion Pharmaceuticals in early 1999. And he's been there ever since, I guess. He's risen up through the ranks and has significant responsibilities. He's been involved in a number of major programs in endothelin antagonists, oxorexin receptor antagonists, etc., many of which have got clinical candidates, indeed marketed drugs. But for the last 10 years or so, he's been involved in the Malaria collaboration. It's that work that he's going to talk about today. Discovery and characterization of ACT 451840, an anti-malarial drug with a novel mechanism of action.
Good afternoon, ladies and gentlemen. Thanks, Chris, for the very nice introduction. So you just heard I was working with Actelion Pharmaceuticals over the last almost 19 years, and now you see Idorsia here. So you may wonder why Idorsia. You may have missed that. It's a very new company. The company started to exist in the middle of June this year, and it was actually a consequence of the merger between Actelion and Johnson & Johnson, where the whole research organization of Actelion was spun out into a new company called Idorsia. This still doesn't tell you why a company like Actelion had actually a program in the field of antimalarials. As you just heard, we were mainly interested in treatments for pulmonary arterial hypertension, where we were also quite successful. But on the other hand, we were also interested in aspartic proteases as drug targets, such as renine or BACE, or, for example, the parasite protease plasmepsin-2. At that time, plasmepsin-2 was the easiest to produce and the easiest to crystallize. So we thought we would work on plasmepsin-2 in order to have a positive impact on our other aspartic protease projects. And we then could immediately convince our management that we would like to hire master students to do all the chemistry work on that. All the biology work was done at the Swiss TPH. But after a certain time, the community found out that actually plasmepsin-2 is not a target which is relevant in order to kill the malaria parasite. So we sat together with the Swiss TPH, and at that moment, the people from the Swiss TPH proposed to us that they would screen 5,000 compounds from our corporate library, which we could freely select in their red blood cell assay, and then we would see what happens. And actually, what I'm going to tell you in the next 30 minutes is the consequences that came out of this screening. So we will learn what we identified in the screening as the screening hit. I will briefly explain to you the optimization of the screening hit into the clinical candidate. Then we will describe a bit, or we will hear a bit about the phase 1 clinical study and the malaria clinical study. And I will start with a very, very brief and very, very quick overview of malaria, as we have just heard from Kelly, how all the details there actually work. So, as you have heard, malaria is still, together with tuberculosis and AIDS, one of the world's leading infectious diseases. It's caused by Plasmodium parasites. We have heard 5 different species are existing, and the most lethal one is actually the Falciparum parasite. It's the most widespread parasitic disease in man. So the number here is even higher, as we have seen from Kelly's talk. And the Falciparum parasite causes most of the malaria-associated death, and it's mainly located in sub-Saharan Africa and 10% in South America and Southeast Asia. As we have seen, malaria affects drastically the functionality of societies and has very negative consequences on the economic development. When you look at this picture here, actually the major statement I want to make to this kind of picture is in the year 2000, we had 106 countries where malaria was endemic. In 2015, we had 95 countries where malaria was endemic. So we are moving in the right direction, but we are not yet there. Let's focus on this one, this line on this brief statistics here, which confirms actually what we have seen in the former slide. So the number of infections in the year 2000 was in the area of 260 million and is slightly decreasing over the last 15 years to close to 200 million, so a decrease of about 20%. The decrease in deaths associated with malaria is more dramatical, is about 48%, but it's still more than 400,000 people who die every year from malaria. So there is a lot that needs to be done. Why is it still a very serious issue in our world? So I think one of the aspects is the increased mobility of the population, which might lead to more efficient distribution of the parasite, probably climate changes, agricultural habits which change, political conflicts which actually work against the people who try to distribute the malaria medicines. And then we have observed mosquito vectors which start to become resistant to pesticides. And then just recently, first resistances against artemisinins are now confirmed. The very complex malaria life cycle, I'm not going to repeat what Kelly just said. You just heard you have an aspect in the mosquito, you have a very important aspect in the liver, and then you have an aspect in the blood, where we actually work from trophozoite to schizont and then to rupture schizont, and here actually you notice the symptoms of malaria. What does an anti-malarial drug need to fulfill? So it needs to be active against Plasmodium falciparum, chloroquine sensitive as well as chloroquine resistant strains. A very fast onset of action is certainly an asset. It should be structurally different from marketed antimalarials, and it should be chemically stable. We have heard the reasons for that, so like there are no fridges, all the infrastructure is very limited. If it could have a potentially novel mechanism of action, this would certainly be a huge asset. This is probably linked to the structural differences, which could then enhance the probability of a different mechanism of action. Low cost of goods, orally active, 1 to maximally 3 days of treatment, best would be 1 dose, and you have a cure. You should be very careful about parasite resistance. It needs to be suitable for combinations with other antimalarial drugs. I think in the field of malaria, the future will remain that you use combinations of at least 2 drugs. And the safety profile of the drug needs to be very high, because you need to be able to use it in children as well as in pregnant women. So the requirements are at least as tough as in any other drug discovery project. So the screening that I already mentioned of these 5,000 compounds resulted in this hit. Why was this hit attractive to us? Mainly because of the activity that the people at the Swiss Tropical Institute observed. So it was in the area of 4 nanomolar in their red blood cell assay against K1. When you look at this compound as a medicinal chemist, you see immediately a lot of options where you can work on. So you have the amino acid in the middle, so there is a lot of things to do in this area. You have the cinnamic acid in this part of the molecule. We certainly want to know what the influence of the double bond on the activity is. You have potential to investigate the substitution patterns. When you see a pentyl chain, you probably want to replace it by something more drug-like. Then you have a center of chirality, which needs to be clarified. And certainly also in this area, the molecule asks for easy optimization of the situation, and probably you would also like to think about where to reduce a bit the size of the molecule. Synthetically, it's very simple, which can be an important asset in the field of drugs for neglected diseases. So a simple amide coupling, then a deprotection of the Boc group. The next substituent is introduced by reductive amination, and the last substituent can be introduced by an easy acylation. We have protected these compounds in several patent applications exactly for the reasons that were already mentioned. The main reason why you patent these approaches is to guarantee for yourself freedom to operate. Nobody else patents it away from you and stands in your way of what you want to do with the compound. So the first thing I want to clarify with you is the influence of the center of chirality on the activity. You can see here you have the natural amino acid, here you have the unnatural amino acid. The natural amino acid actually results in the active compound, the unnatural amino acid results in the less active compound. A first important advantage to us, because the price difference between these two is huge. Then next thing that needs to be clarified was the substitution on this phenyl ring. When you compare these 3 compounds, you can see that the para-substituted as compared to the meta-substituted as compared to the ortho-substituted results in the best activity. So para-substitution in this area is preferred. Next, we try to find out whether we can replace the cinnamoylic part of the molecule. When you go through this table, you will find out that reduction or elongation or implementation of the linker into a cycle, reduction of the aromatic system, replacing it with a smaller one, or just only having an alkyl chain or a small cycle, actually results in much less active compounds. And the only compound which showed significant activity was this indolyl propionic acid, but if as a medicinal chemist you have the choice between an indole and this unit, you would probably focus on this unit. So then comes the question of whether the double bond shows Michael-acceptor reactivity. So we clarified that by generating derivatives which have highly electron-rich aromatic systems and less rich aromatic systems. When you compare the activity, you see that the activity for all these kind of variations is the same. And we did Danziel trapping experiments with all these compounds, and we observed no trapping. So by this, we would say that the cinnamic acid moiety does not show Michael-acceptor reactivity and is not important for the activity because of that Michael-acceptor reactivity. Then the next thing we wanted to investigate was a little bit in the area of the pentyl-benzyl replacements, as shown here. And you can see here that actually many things are possible and give you decent activities. But what you see on this slide as well is that we started to characterize the compounds in different assays or under different assay conditions, because we found actually out that the assay conditions, the standard assay conditions in Albumax for the K1 and the NF54 were sometimes misleading. And then the Sergio Wittlin's group at the Swiss TPH established assays where they added 50% of serum to the assay media. And this was much closer to relevant conditions later on for in vivo investigations. And actually, we often assessed then our compounds also based on the shift between the two assay data points in the K1 and in the NF54. So compounds with a lower shift might be better than compounds with the maximal activity. Another thing which becomes obvious from this slide here is we were in the unfortunate situation that actually our compounds did not translate their activity against the human parasite into activity against the Burgeye parasite very often. This makes it a bit more complicated to actually assess the compounds pharmacologically in the standard Burgeye mouse model. So we also investigated the area of the amino acid. So we tried to find replacements for the phenyl ring in the phenylalanine core of the molecule. You see that we replaced it with saturated heterocycles such as piperazine, morpholine, piperidine, then also aromatic heterocycles such as pyrimidine or isoxazole here. And we also did a fluorine scan on the phenyl ring. And based on all that, you can see that with all these transformations, we did not really identify significant advantages to the simple phenylalanine. So we stick to the simple phenylalanine for the future. Then actually, we never asked the question so far whether the phenylalanine is at all necessary. But when you cut it off completely, you see that your compound is or loses all the activity. Then actually the question also is whether the CH2 in this position is the best, or you could maybe have something else. So we elongated the chain, we lost a lot of the activity, we reduced the chain to phenyl-lysine, same picture. So actually the phenylalanine really seems to be the best core in these compounds. We then started to ask ourselves questions about the potential introduction of substituents at the benzyl piperazine part, and based on the results that are summarized here, you can see that substituents are tolerated, heteroaromatic systems are or could also be tolerated. The introduction or the reduction of the basicity of this center by introducing either a carbonyl group here or here is not really of any advantage, especially not in the NF54 serum assay, and the elongation of the chain also results in a reduction of activity. Then we did all the obvious replacements of the benzyl piperazine, so 7-membered ring, sulfonamide on the piperazine, replacing the piperazine by aminopyperidine or by the inverted aminopyperidine, directly attaching a heteroaromatic system to the piperazine, replacing the piperazine by an open chain morpholine isoster or by a morpholine or by more fancy piperazines did not result in any significant advantage as compared to the benzyl piperazine. So this made us remain with the benzylpiperazine for the future investigations. We came back to investigating more about the substitution on the benzyl ring of the benzylpiperazine, and by this effort summarized here, we found a compound which looked to us very interesting, which we wanted to further characterize, having this kind of nitrogen and this ethanol and methyl group linked to the nitrogen. So we wanted to characterize this compound more broadly, together with the collaborators from the Swiss TPH. So this compound had the number ACT213615. We wanted to find out how efficient it acts against resistant parasite, how fast it acts, and which parasite stages are affected. In order to do that, we did the assessment of our compound against resistant parasite strains, which are summarized here. And you can see that the reference compounds here behave exactly as expected. So when you have a resistancy indicated, they are more or less inactive. When you have no resistancy indicated, as for example here for chloroquine, you still have remaining activity. The only derivative which is still active against all the parasites is artesunate. And when you then measure our compound, you see that actually we have a very nice profile with respect to activity against resistant parasites comparable to artesunate. Then we wanted to find out which parasite stages are affected and how quickly does the compound act. So for this, you need to generate synchronized cultures, which was also done at the Swiss TPH in the biology there. And then they assessed first a reference compound, pyrimethamine. And pyrimethamine, you can see here, is actually not active against the ring stage. Then when you look at the trophozoid stage, you start to see some activity at high dose after a long time of incubation. And in the schizont stage, you start to see beginning activity at high dose after 6 hours, which then increases to medium dose, nice activity after 24 hours. So summarized here, you see that actually pyrimethamine is only active against late stages of the parasite. We did exactly the same experiment with our compound, and this was the picture we obtained. We were very happy about this picture because you can see that actually our compound at high dose is already nicely active against rings, trophozoites, and schizonts after very short time, and at low dose it's active against all stages after 24 hours. So it acts very rapidly against all stages. And this is actually summarizing just what I described to you. I just wanted to put it on one slide because it actually looks pretty cool. So this is pyrimethamine, and, and this is our compound. So the picture is really much better with our compound. We then investigated our compound still, even though it was maybe not optimal for mouse experiments. In mouse experiments, to have a result on a proof of concept whether we could cure mice with our compound. We dosed up to 750 milligrams. It was dosed 3 times on 3 consecutive days. And by doing this, we could actually make the mice survive for 30 days. And 30 days in this kind of setting is considered as cure from malaria. So our compound rapidly kills all asexual blood stages of the parasite, and it's very active against resistant parasite strains. It's active in the Burgei mouse model, and we also investigated the compound in the SCID mouse model with the connection of the Swiss TPH to GSK Tres Cantos, where the experiments were done. The mouse model was already described by Kelly, and there actually we found that our compound showed an ED90 of 8.4 milligram per kilogram, and the standard control chloroquine in this experiment is a bit more efficacious. So we were somehow in the middle of something. We wanted to do better, so back to the lab. A few other rounds of optimization, which I summarize with just a few compounds in this slide. We worked again on the cinnamoyl group in this last round of optimization. We kept here the nitrile substituent fixed. the phenylalanine, and this was also identified as the best substituent in this area, combined with a para-T-butyl substituted phenyl ring in this position, resulted in the compound that was considered by the team as the best compound to further profile. We then started by profiling this compound again in the Burgei mouse model. And here we start to see when up-titrating the dose at 20 mg once a day, one dose, we start to see a significant activity. We needed to go up to 300 milligrams per kilogram on 3 consecutive days to obtain a cure of the mice, but which was already much better than the compound that I just described to you before. We investigated the compound in the same way as the other compound against a panel of resistant strains. This was done in the lab of David Vidok in the US in collaboration with the Swiss TPH. And you can see again the same picture as before. ACT 451840 shows more or less comparable activity against all resistant strains as artesunate, and is much more active than chloroquine or pyrimethamine. The picture that you have seen for the other compound on the stage specificities is the same for this compound, or even more efficacious. So you can actually see that after 6 hours, the intermediate dose is already fully active against all stages, and after 24 hours, already the very low dose starts to show activity against all blood stages of the parasite. Then the compound was again profiled in the Plasmodium falciparum infected mice, and I just summarize here the reduction in parasitemia over time. So you actually infect the mice, you start treating after 3 days for 4 consecutive days, and you see that we start to see significant activity with our compound at 10 milligrams per kilogram, and then even a bit better activity at 30 and at 100 milligrams per kilogram. So preclinical conclusions about ACT 451840. So it exhibited an IC50 below 10 nanomolar in vitro against a panel of sensitive and resistant strains of P. falciparum, which is already a positive asset. It showed ex vivo activity against falciparum and vivax. It had about 3.7 milligram per kilogram ED90 in the P. falciparum mouse model, and it inhibited the growth of all asexual blood stages of P. falciparum. This might, after what we have heard from Kelly, not yet be enough, but that's certainly already a nice asset. We then decided, together with the Swiss TPH and in collaboration with MMV, to do some clinical work with this compound. So the compound went into a clinical phase 1 study, 40 subjects. It was a single ascending dose study to investigate safety, tolerability, and pharmacokinetics. That's what you always do in a phase 1 study. And these were the doses administered, 10, 50, 200, and 500. And in the 500 and 200 dose groups, it was also investigated for food effects. With respect to safety and tolerability, there were no reports of serious adverse events or adverse events leading to discontinuation. Only 2 subjects out of 30 reported adverse events like headache, nausea, and vomiting. And extremely important, no clinically relevant ECG findings, so no cardiovascular side effects were reported. On this slide, this is the drawback of this compound. I only want to point out 3 little things. So PK-wise, you can see that you have a nice dose proportionality. Then here on this side, you have the dose group which is fasted, and here on this side, you have the dose group which is fed. And you can actually see that when we have comparative data, so in the 200 and in the 500 milligram dose groups, the Cmax increases by a factor of at least 10 to 15 in the fed group as compared to the fasted group, which is, as we have heard before, a drawback in anti-malarial drug discovery. So we still continued with this compound in an induced blood stage malaria study. So this was done with 8 healthy male subjects, which were infected with blood stage P. falciparum, and after 7 days, they received a single dose of 500 milligrams of ACT 451-840 under fed conditions, based on the results that we have seen from the phase 1 study. And then drug concentrations and parasite load were determined frequently. And the results were that the compound was very well tolerated and safe. A single dose treatment significantly reduced the level of P. falciparum parasitemia. A curative dose estimated would have been 300 milligram for 6 days. To compare that or to put that into relationship, artesunate monotherapy under these conditions would be reached cure when you dose for 7 days. So the single dose treatment did not fully fulfill our hopes, but based on the results we obtained, we still think that this compound could be an interesting asset to be investigated in combinations with other antimalarial drugs, especially as maybe an artesunate replacement. So the chemist's conclusion. We optimized based on several phenotypic assays our hit 1 into the clinical candidate 44. What might be a bit frustrating about that is that actually the clinical candidate structure is pretty close to the hit structure. We would have hoped that we get a bit further away from the hit structure, also to have a bit more space to optimize our compounds. But in this area, we could establish a clear structure-activity relationship. The in vitro assay conditions we have found out are of key importance to estimate the potential in vivo activity. So this kind of step where we started to assay our compounds in the presence of serum really helped us to move more efficiently forward. We have also found out that our compound 451-840 behaves similar to artemisinin derivatives, so very fast onset, efficacious elimination of parasites, and also short duration of action. And then maybe the last conclusion from the medicinal chemist, so high molecular weight compounds, which are certainly highly lipophilic, always result in difficult to predict PK behavior. So if you can go for smaller compounds, go for smaller compounds. So the anti-malarial drug discovery at Actelion was a very efficient and true collaboration over more than 10 years with the Swiss Tropical and Public Health Institute, which is also located in the same area. So they are located in Basel, we are located in Allschwil, so we have 5 minutes to get to each other, which was very, very efficient. And this whole work benefited a lot from the excellent connections that the Swiss TPH has into the world of malaria drug discovery. We would never have been able to reach what we reached without them, so they were really key in organizing the further characterizations of the compounds and all these things. And with that, I would actually like to thank many people that were involved in this endeavor to identify 840, and I would like to thank the organizer for the invitation, and I would like to thank you for your attention.
Very, very nice talk. Thank you very much. Any questions?
Thank you for a really nice talk on a very important topic. So I noticed when you add serum, you have a serum shift that is perhaps 5-fold or something like that. I suspect your plasma protein binding is in the 99 something. So you actually have less shift than protein binding would suggest, which is something that happens many times with antibacterial. The free drug hypothesis doesn't seem to always work. Do you have any explanation, or do you have a working model to go around that?
Personally, I don't have an explanation. I think the free drug hypothesis is a very logical hypothesis and should be taken into account whenever you can. But I also think that in certain projects, if you have this kind of possibilities in biological assays, then personally I would focus on the outcome of the biological assay and neglect a bit the plasma protein binding, because I think that's much more relevant for future in vivo behavior. At least what we have seen in this project is predicted nicely which compounds we should profile in vivo and which ones we should just forget about them.
I noticed you showed us a very big food effect in phase 1, and I wondered if you had an understanding of whether it's linked to solubility, permeability, and whether perhaps a different formulation might give more consistent and enhanced exposure in humans and improve the efficacy.
Yes, so we investigated a lot into this direction, and as you can imagine, these compounds, just based on their size and on their molecular weight, solubility was not one of their strengths, so that's why I didn't address this topic actually during the talk. We investigated the food effect in different settings in animals as well, and when you just formulate your compounds with a lot of fat, with oil or with whatever, you have better absorption. And I think it's exclusively due to the lipophilicity and the bad solubility of this compound that you see this effect, and by all the formulation work we did, we could not overcome it, and I think it also proves that formulation can do something, but if you are really in trouble, it's not going to save you.
When you started off the talk, you started talking about the protease targets. Do you have a feeling that that is the target that you're dealing with, or is it definitely a different target? Or you have no idea?
We have done certain investigations on target identification. We have also published a paper on that, and we have come to the conclusion that the target is probably an efflux transporter of the parasite. So we inhibit an efflux transporter of the parasite.
Okay, I think in order to keep on time with the webcast, we'll finish there. Thanks very much for the talk. Perhaps you could join me in thanking both speakers. Okay, we'll resume at 3:10. Will the flash poster presenters for the next session remember to come and sit in the front row, ready to do their thing afterwards? Thank you. Okay, I think we should start the next session in this webcast. First speaker in this session is Rob Young. Rob joined Wellcome in 1990 and has stayed through various changes, mergers, name changes, etc., acquisitions, and has made significant contributions to 6 development candidates in a whole variety of different therapeutic areas. He moved to the early stage discovery in 2006 and his collaborations across numerous hit-to-lead programs. He has strong links with the group in Tres Cantos, and through several projects and mentoring roles served on scientific advisory board for Project Orchid, a new EU-funded multidisciplinary multi-centre tuberculosis programme. He's an honorary visiting professor of the University of St Andrews and is also a fellow of the Royal Society of Chemistry. This afternoon, Bob's going to talk about the rapid discovery of non-covalent inhibitors, or DPRE1, a novel and exciting target to treat Mycobacterium tuberculosis, impact on medicinal chemistry on an open source collaboration.
Okay, thank you, Chris, and thanks to the committee for giving me a chance to join this excellent symposium. So I've got kind of a funny relationship with tuberculosis, because I wouldn't actually be here but for TB, because my mother moved out of Wales into Somerset, and she met my father in a hospital that was built for TB patients. So I've got one thing to thank it for. But plus, it's brought me in contact with so many wonderful people over the last few years. And it's my privilege today to speak on behalf of the DPRE1 team. So if you look at what's in the brochures, it tells you it's not just the MedChem, so there's a little bit, and you'll expect a few things in there from me that, in the way we did things. But there's also some cool things that I think are good lessons for anybody on a medicinal chemistry program on making sure you've got the best assay and the best understanding of your assay, and we'll see this as we go through. So this is some open source drug discovery. We'll show you how GSK published a group of compounds, went into academia, and Del Bezra's group identified the target for one of our compounds. So in the early stage of the program, fine-tuning the assays and just a little bit of thought being put into that enabled an HTS, and it saved us I don't know how many tens, hundreds of thousands of pounds and time in setting up the assay. The then bit is lead hopping, and if any of you have read my papers in the literature, you'll see fragmentation and lower fat chemistry as being my central ethos in how I do my medicinal chemistry. And we'll see how we got potent in vivo activity. And this is the first disclosure of the lead exemplar from our series. So I take you as far as the end of hits a lead. I'm afraid I won't be able to disclose anything beyond that. I guess in the spirit of an open session, we probably should, but I've not had that conversation with Tris Cantos, and we'll have to leave things there. Also at the end, there's some really cool stuff in terms of mode of action studies. So with Archie Argyro, who now works for AstraZeneca, he enabled some really cool enzymology that showed some real insight into the mode of action of this enzyme. And it's also, as I said, a big learning for many of you in your programs. Just be careful that you don't fall foul of this kind of thing. So Kelly eloquently set the scene, I guess, for TB, so I probably don't need to go through this slide in too much detail. That TB lives with us. You know, we're vectors, and we often end up as victims. This is a thing I particularly like. 1 billion people have died of TB. It's the biggest killer in history. Yet it's still a huge problem now. You know, we all dig through the World Health Organization reports. You know, still in 2015, over 1 million people die from it, as we've seen. All the infections and the new cases, as we heard before, MDR-TB, especially exacerbated by co-infection with HIV, especially in sub-Saharan Africa. I love this quote. The WHO described as MDR-TB as Ebola with wings. That's sort of the level of threat. So this, again, is a sort of thing we've seen in the previous discussions, but these are the kind of patient populations we have. 4 drugs, 6 months of therapy, not particularly pleasant, just an 85% success rate. That's if you have drug-susceptible TB. We need a shorter symptom therapy. Drug-resistant, as we heard about before, only 50% success. You're out to maybe greater than equal to 18 months. The little letters here, the capital letters, are the combination of drugs that are typically used. Co-infections with HIV just makes it even worse. You get a lot of drug-drug interactions when you have these kind of therapies. So we need a compound. There are new compounds on the market. I've not gone through some of that, but that's kind of well reviewed in the literature. Hopefully, as we go through, I can focus a bit more on our science. Although I do like this slide, just so it puts Kelly's comments in perspective. That's what you take every day if you have susceptible TB. Can we take this to one of the villages in South Africa that's a long way away from the nearest hospital? That number of pills when you're not feeling very well, you've got to swallow that lot. And I remember seeing a program about it. These people can't swallow, let alone swallow that much medicine, plus an injection. That's the current situation with facing people with MDR-TB. So, fast forward to DPRE1. So decaprenyl phosphoryl D-ribose oxidase. So this is DPR, decaprenyl, coming right across the board. It's a pretty big molecule. At the end of it is a phosphorypose. This is Mycobacterium tuberculosis' only source of arabinose. And the arabinan is an absolutely essential part of the TB cell wall. DPRE1 comes in and oxidizes it to DPX. So you get the ketone here. DPRE2 is a reductase, which takes us down to the arabinose, and then this is subsequently cleaved. It's believed that this sits in the cell membrane. There's some elegant studies by Stuart Cole's group that shows the location of the enzyme, so you don't have to get all the way into the TB through both cell walls and the big thick coat that's outside it. So it makes life a little bit easier. The inhibitors are active against MDR and XDR strains of MTB, and it's absolutely essential. So DPRE1, that is. DPRE2 isn't, but DPRE1 is essential for the viability of mycobacteria. Compounds related to BCZ043 are in the clinic for TB. This is a covalent inhibitor. There's plenty of data on how this binds and how it works. It's a fairly susceptible compound, but resistance does come to this compound. So a well-precedented target, well-validated. We sort of moved into it about 4 or 5 years ago now. And we wanted to start setting up a program to do our own screen. But at that time, so this was through ORCID, which I was part of, as Chris said, Del Bezra's team had this overexpressive strain, so they've knocked up the DPRI1 in BCG. And this little graph here and the changes in activity show that when you overexpress DPRI1, the activity or the MIC of the compound goes down. And that identified DPRI1 as the target of one of our compounds. So this is all published, so I won't labor too much on that. The compound that I'm talking about here is GSK 710. So this is published in the paper. And this is one, as I was saying before, from the open source set of compounds. I believe if you get in touch with the guys in Tres Cantos, they will send this out to people, and people can do studies on these and try and work out modes of action of the other 170, I think now. There are several more that have now been elucidated. Key thing about this compound is it has an MIC. The hardest thing in most of these parasites is translating activity against an isolated target into an MIC. We'll say more about that in a second. So, a place to start. I'll click the right button in a second. So, when this was published, Luis Valel asked me to make a comment, because there have been various things in the literature about the quality of some compounds that have been put in the public domain from industry, from other sources, sort of suggesting that they may not be quite as good as they say they are. So I did an analysis of what was in the TB set, and sort of talking about the distribution of lipophilicity and aromatic rings. So if you get to any optimization program, you might want to pay attention to decreasing your lipophilicity or minimizing your number of aromatic rings. It would be a sensible approach, because although most of the compounds are in a reasonable place for lead optimization, but don't forget all of these compounds already have an MIC. So one of my views at the moment, I like being reactionary, but I think we've got to stop as a medicinal chemistry community going back to the rule of 5. It is so last millennium. I'm afraid, what I say about the Lipinski rule of 5 is weight does not matter. We talk about all these things. We saw the compounds this morning. Sulfonamides, fluorines all over them. They're very heavy atoms that aren't very big. So Alan Hill, who's my great partner in crime, looked at CMR, so calculated molar refraction, 30 years ago at Wellcome. This led to the development of naratriptan, very neglected work. That describes the size of the molecule. I believe that size and shape are two of the key things that happen here, and that will enable you to get into TB. I'm also a heretic when it comes to going through cells. I'm in the Doug Kell school quite firmly. I believe everything goes in on protein. Not necessarily an active protein, but it's more likely to go through on a protein than it is through the membrane, using his argument. And all the data that I've seen kind of backs it up. Well, it doesn't disprove it, but it doesn't prove the other one either. But I still think with TB, if you've got something that gets in of a certain size, a certain shape, you're in a good place. So size, and the thing that will appear on my gravestone is PFI, which is the summation of chromatographic log D, which is what we use now as the standard in GSK. And I see lots of other people on their posters at the moment are using chromatographic measurements to estimate hydrophobicity. They aren't really good. If you add that to the number of aromatic rings, this very simple addition, it has a huge effect on many of the things that affect the developability of compounds. Look at the paper here for further details. I won't say any more, but you will see it in a few more GSK presentations and posters. So this is the graph of describing the lipophilicity plus aromaticity against CMR. And this is a remarkable way of sorting the wheat from the chaff in terms of oral availability. And this is the set of 177 compounds. They're superimposed on oral drugs with a bioavailability of 30%. I'm afraid it's not very visible here, but if you look in this paper, you'll see that there is a reasonable degree of overlap. So that's the sort of place that we want to be. Although at the moment, with here, we've got a huge PFI and a low solubility, but we'll come back to that in a second. So before we can start screening, we had an assay, and this is published in the paper, based on farnesyl phospho-D-ribose as the substrate. So this is nicely turned over by DPRI1. It's coupled to risazorin, and it's a flavin. There's a flavin in the enzyme, and that was a way of running an assay, and other people have done this as well. But working with Steve Ratcliffe and some of my colleagues in Spain, we worked out that if we got a bit longer and a bit more lipophilic, we might have a better chance. This is the rate of enzyme production against the concentration of substrate. So focus at the moment on the red line, and then on this blue line. This is the effect of having GGPR. So you can see at this level, and this is quite a range of concentrations, it just shows how much higher the rate is. So i.e., you can drop the concentration of enzyme down, you can use a lot less substrate, and this is what saved us tens, hundreds of thousands of pounds and time in running our high throughput screen. So just a little bit of thought from medicinal chemists, tools chemists, can enable your HTS campaign and make things a lot better. So it was 6-fold less protein was the difference. We'll come back to the other ones later. So we had a target. These are some cool things that the guys in Lausanne did in terms of, if you look at the paper, you will see some movies of the compounds killing TB, and we had an assay. So we needed to move on and go away from this compound. So I was walking in when Paul Leeson did his time at GSK as a consultant. We became the best of friends, of course. I said to him, you want to see what we've just done against TB? I said, we start with the compound, and I sort of said what the properties were, and he just said to me, you should know better than that. And I just said to him, Paul, I disagree. And we've hotly debated this ever since, and we're in the middle of a review that will describe the kind of thinking that we're doing here, just looking how programs progress and how can we benchmark where we're going in medicinal chemistry programs. It doesn't just apply here. So as I said, we've got pretty poor properties. Needless to say, it's insoluble. They did try it in the mouse model in Triscanthos. There was no efficacy. Amongst our collection, we had a prune version, so we can take an aromatic ring off. You can lose a lot of lipophilicity, and a little bit more soluble, but still not that good. But importantly, we still had an MIC, so it was looking interesting. So at this point, where we had about half a dozen compounds in the series, we decided with myself and Ian Wall to do a little bit of lead hopping. And we did a similarity search, and it threw out this compound that was in the collection. We bought a couple more in from one of our external vendors. The activity wasn't so far away. Importantly, we still had an MIC. And I guess most of the people in the room have been turning their noses up at a thiazole and God, heterocyclic dyslexia strikes again, but a pyrrole. Yeah, so, they're not the nicest of molecules, but we managed to get pyrimidine and a piperidine in there. And we went quite quickly as we went through the first bits of SAR. To me, all good drugs have a morphine in. Some people don't like them, I love them. And again, we're still getting reasonable levels of activity, still an MIC, but you can see our PFI is coming right down. We grew back out again, we went to an isopropyl group, the activity went up a little bit. We got back to the whole length molecule. And now we're starting to get to reasonable MICs. PFI is, whether it should be 6 or 7 is not bad. The ligand efficiency, which I think is the most important thing in molecules, is by and large maintained through the series. So all of these data are in the GGPR assay, as opposed to some earlier ones which were in the FPR. So Jennifer Borthwick by now was on board doing some of this, and this was for her stratified PhD, so another common theme with GSK talks. So we went from 932. I was about to send an outsourcing request in, and this one came back, and unsurprisingly, it had quite high clearance. So I said, well, we just put a parafluoro in. We do that, we block the metabolism. The MIC came down, the activity we can't tell because we're at the top of the assay. But we also did things like improving the properties by putting an oxygen into the molecule. So as a hit to lead place, and something to hand over to our colleagues for further optimization, we're not in a bad place. So I've been talking about journeys. So where we want to be is somewhere with a reasonable level of activity. So I put 7 as a line in here, so at least that. The red line is the tight binding limit of the assay, but I've just reported the numbers as they've come out of the assay in line with GSK data integrity requirements. And it just sort of shows this plotted against PFI. And if you like, there's a number of parallel lines across here, which are the equivalent of LLE or LIPI, but using PFI as the thing you take away from your potency. One of several graphs I think is important, along with the one I showed you earlier. So if you look at the journey that we've done there, we started up here as we've truncated. But as we did this, we were still in that position where we were staying reasonably active. And if I flick back, this is colored by the levels of where we're still seeing an MIC at certain levels. One of the things that Jenny worked on as well was actually fragmenting these right back, and we could still see activity in this compound and a reasonable level of ligand efficiency. So that provided a basis for some fairly rapid optimization of these compounds. And as you can see, there's just a couple of SNARs and an amide coupling, and we've got fairly cheap compounds and should be a low cost of goods for any final compound. So you can see as we grow back, this is the kind of growth vector that we got to get to some of our better compounds. So a bit of a hopping from what proved to be a false positive in the HTS was this compound down here, and Ben Whitehurst is in the audience somewhere. took this as part of his PhD from Strathclyde as well. And you can sort of see that with this one, with the piperidinone, we could go to, we were on a vector to grow to much better compounds somewhere near the promised land. So we had a compound here that was in even better space. The GSK guidelines for this, as it's published, is a PFI of ideally below 6. So this gave us a set of compounds like this with potency, reasonable MICs. Some of them were particularly potent in an intracellular MIC where the bacterium was growing within the macrophage. Some of the properties are in a reasonable place. HSA, not too bad because we're in slightly better property space. Passive solubility was sort of on the edge sometime, but when we went to the ones with the extra oxygen in, which are less lipophilic, even better. One problem with those compounds, we've probably got too hydrophilic for the size of the compound. We've got no permeability, and these compounds were inactive. But these compounds also were a lot cleaner in various assays. So in the cytotoxicity HepG2 assay, they were more effective. So the clearance varied, but again, as the properties got better, we got better clearance. So we took some of these compounds forward to the acute mouse model that is run in Triscantos. So this involves treatment of mice, and you get an exponential growth of the number of bugs in the lungs, and eventually that gets to a steady state. And in this form of the assay, as published by Joaquin and his colleagues, we treat during this exponential growth phase. So we want to see what the efficacy of our compound is there. So the compound is treated for 9 days. There's euthanasia of the mice, and then the lungs are plated, and people look for the number of colony-forming units that are left after treatment with the drug. So we did a comparison between one of our compounds that hits the lead stage, and by then, AstraZeneca had published on this series. This isn't the best of the compound in the series, but it was something published that we could benchmark at the time through the GAP-B collaboration. So these are the results. With our compounds, we dosed them straight away. In the publication, this AZ compound was co-dosed with ABT, which is a P450 inhibitor, to get extra exposure. And you can still see without it, this compound is relatively inactive. But with ABT, this compound, obviously, you get enhanced exposure of the drug, and it's just slightly more potent than ours. But nonetheless, 29 and 30 mg per kg EC99, so that's a 2-log drop of bacterial load was achieved with the compound. So, we were very pleased with this, and it was a good place for further optimization. An additional assay is the chronic assay, whereby you do your treatment in the stationary phase. And I guess most people who get to the clinic are in this phase with TB, rather than being caught in the exponential growth phase. So, took me by surprise. The compound was dosed over, there's some vestiges of animation in there, the culture plate. So we have a 2-month treatment course of the compound, so dosed once daily. Without pharmacokinetic particular measurements. That's one of the things that the Triscantos group do. They go straight into the animals without extensive evaluation, although this one was looked at a little bit from the acute study. So again, the compound was efficacious, so 588 was taken forward, and it had an ED99 of 143 mg per kg in this more challenging assay. So again, we've achieved a good treatment and an effective outcome with these particular compounds. So this is just a benchmark for where we were with the series. So you can sort of see, a number of the marketed drugs have been put through this assay. Obviously with TB, you're likely to end up in a combination. And this was the profile of our two compounds and how well they stood up. So as I said, this has been taken further. I'm sure in due course more further information will come out on where we go next with these compounds. I know one question that will come will be about resistance. I know we've struggled to make any resistant mutants against these compounds. So it's an important feature of them as well. So there's the HCD chemistry part. So we'll just go off on another tangent a little here, but some lessons for kind of other medicinal chemists. So one of the compounds from the HTS was this compound GSK162. And one of the problems we had at GSK most of the time was getting a reliable crystal system. There are structures out there, and there's a lot of variety in the way the structures work. And there's a nice paper from Stuart Cole's group describing various different structures, and we've got plenty that complement that and further understanding. So this is how this compound was bound. So we looked at this and thought, well, this methyl group off of here and off of the meta position here of this ring ought to be a good chance to hang an FP ligand. So we thought we could get an FP assay, just a binding assay to see how the compounds are working. So you can see we took one off the methyl group, one off the meta position, so Steve Radcliffe doing all of this. And our group in Boston had discovered a series akin to this compound, and we also made an FP ligand off of that. And you can see Archie's work on the FP signal against the concentration of DPRA1. So we can sort of see that 366, the compound coloured green here, was the tightest binding one, and or the lowest KD, and this is the one that we took forward as a putative FP ligand to see how things would work. So you've seen how that compound bound, and all of a sudden, so in the literature, has been TCA1 from the group at Scripps, the AZ compound, one of ours, and the FP ligand. You can see the FP ligand and TCA1, they look fairly similar. They're still active. But this compound and ours, all of a sudden, the activity has gone back a long, long way, and there's next to no activity in there. But what we discovered, that when we added our substrate in there, GGPR, suddenly the activity was coming back. We'll come back to that. I talked about these curves, and the observant amongst you will have noticed that when we see DPRA1, the whole structure, it's all Z. If you could buy FPR or GGPR from Aldrich or wherever, I guess they're related more to the mammalian systems, and they're all E configured. So we finally got to the 5. We made all 3. So the Z, FPR, GGPR, and the pentoprenyl. This was a heroic synthesis from our outsourcing group. But Ben managed to make this substrate, and we did make some other analogs as well. But you can see here, we've got an even better turnover, so the chance of an even more sensitive assays. So when we got to this, we now got to the point we could work out with a high tight binding limit, we could get a better handle on the concentration of our compounds. So there's a comparison of some of the various compounds in this talk, including the competitors. So you can sort of see that we've got a lot of these compounds, sort of teens of nanomolar on here. There is a detergent effect. I should have pointed out that the reason that these all crash back down again is that we're beyond the critical micelle concentration of these detergents, which our compounds essentially are. I think of an acidic group with a long greasy tail. So they tend to form micelles, and that's one of the big reasons why we lose activity. It isn't kind of a feedback inhibition mechanism. So on with this and having a more sensitive assay, and we could understand better what our true KIs or IC50s of our compounds were. Archie then went to some quite elegant mode of action studies. So he was dropping the level of the substrate right down, and then looking at the IC50 based on the levels of the substrate for a couple of our compounds. So here's 162, and it behaves in a fairly simple competitive manner. But if you look at the Nike tick of a curve we get for our series, you can see that very low levels of substrate, the compound is tending towards being inactive. And as an experienced enzymologist, Archie said, this is unprecedented. And it was the same in both MTB and C. bovis, which we'll come to in a second. So really interesting, and it sort of just shows us that depending on the form of the assay we're doing, we could have missed this compound. So when you see different forms of the assays, just interrogate what the pharmacologists are telling you, or the enzymologists are telling you. We're always slaves to numbers in chemistry, so here's a good warning sign. Just make sure you really know what's going on in the assay. So Archie's managed to model this. He's used the software called Kintec Explorer, and he's estimated a number of these, the kinetic constants. And the output of this, using this simulation, gives you an answer that is sort of commensurate with the explanation we've got. So the transition from this state where if you just bind, once you bind the substrate, you've then got a chance of binding to this E star with your inhibitor before it relaxes back to the sort of ground state that some of the other compounds will bind against. So a really nice example of how that can happen. And then finally, we got a crystal structure for this. So this compound you might have seen sneak into one of the slides for GGSK480. So we had a thiamorphlene and an isopropyl at the end. And this had the same behavior on both C. bovis and tuberculosis. And you can see that the same behavior. When we got a structure of this, and as you see with several of them, you just see a big, big shift in various residues there. And you can see the green structure here is the one we made the FP ligand from, and you can see there's a tyrosine residue that's just sitting right across the way into the enzyme that our main series binds through. So there's the explanation for why, unless you had the substrate there to put the enzyme into a particular state, you don't get any chance of getting any binding. It could be why we've never seen with this green compound, we never saw an MIC with that. Perhaps because if the enzyme is turning over, it's never in the state that that particular compound needs the binding. So little lessons and really cool enzymology and things that I would like to think as a company that GSK can bring to the party. So you've sort of seen the impact of open source, bringing it into the group I work in, which is the HITSA Leads group, and we had a slot in our portfolio, so we were able to pursue this program. And we do this from time to time. I've just delivered another TB, another multiple TB series for another target right now. So, as an advert for Triscantos, I hope people can take our compounds, bring them back into us, get some of the muscle of GSK behind it, and it will help us on that quest to find new HIV medicines. TB medicines, slip of the tongue there. So, you've seen this, the open source. What you can do as a chemist to save time and money, always sort of challenge what the screeners want to do and just think what you can do to do the best way. I've said my little bit about lead hopping, fragmentation, and just what you get from using lower fat chemistry. We quickly got to a place where solubility wasn't the problem. You might have to try fairly hard to get to these places, but I think not just the neglected diseases world, but chemistry in general would benefit from, I guess, smarter medicinal chemistry. So with that, it brings me to thank yous to very many people, teams in biological sciences, in Stevenage and in Triscantos. There's all kinds of chemists in here, from medicinal chemists. I guess it was just myself, Ben and Jenny. Steve was our tools man, and then we had people doing crystallography, and the PhysChem people all made big impacts on this. And all the people that we work with in Triscantos are a fabulous bunch of people to work with. Thanks to Colin and Glenn at Strathclyde, who helped Ben and Jenny with their PhDs. The ORCID Consortium, which gave some funding toward this, and we got help in some of the studies from Neeraj and John McKinney, and some of these people at later stages in the program. So I'll just leave you with a few of the characters. So if you've got open source, Louis Ballel, I'm sure, is very familiar to many of you in the open source arena. There's Del Bezra, who's a great mate of these guys, and David is the head of the DPU. Archie and myself have been lucky to be in meetings on both sites. This was sadly Archie's farewell down the pub, but these are the guys behind it, and I must thank Birmingham for their help there, the Triscantos Open Lab, and the TB Alliance, who will have brought funding to this program. So thanks for your attention. I haven't talked too long, and we'll take a couple of questions, if there's time.
Thanks very much. Any questions?
Very nice talk, Rob, and some food for thought there. So some of these targets obviously were worked on many years ago, and if you look at the properties of some of the older drugs, for example in antibacterials, they tend to be less lipophilic than what we tend to think of properties for good absorption or cell penetration. So I guess I'm interested to know, now that we've been revisiting some of these classes of targets, but also, bearing in mind the location of your particular target here, whether there's any new thoughts or learnings about the properties of compounds that may be optimal to access these targets, and whether they are different from some of the things we think of more routinely with human kind of cells, because we all know that antibacterials, getting through cell walls is difficult.
Well, my answer to this is, I forgot to say this coming through. If you look at this graph, and if you look at the range of activities and the range of lipophilicity, so we're down here at 5.5 for a PFI, and that's a ring taken out and everything else is on the structure from 9.2. All of these compounds up here are all getting into the cell. So with such a wide range of lipophilicity, I don't think it's lipophilicity alone that drives us. This is where I made the comment. Are we piggybacking on a transporter? That might be a reaction of describing it, but there could be something in there. It's a size and the shape thing maybe, as much as a particular lipophilicity. Because then when you get into, into this space, as much as anything, when you've got activity, you've still got to get the compound into a human and oral administration, and it has to obey the normal rules. So it's finding that sweet spot in between them. I do think with some antibacterials, with some approaches, you need to go a bit higher in terms of properties to get in. But as you say, you go back to the traditional things, and they're the ones that are always off the scale. But I do think where those transporters come in, Mother Nature's made them, and they've had to get to do where they want to somehow, and I just think they've adapted to be recognised.
Perhaps I can ask a quick question. Would you like to comment on tuberculosis in other species? Sorry, it's over here.
Where I'm not looking very well. Oh, sorry, Chris.
Would you like to comment on tuberculosis in other species?
And what the need for drugs?
Yeah.
Or, can I just plead ignorance there?
Okay.
I guess in this country it's the thing about bovine TB and badgers and jumping across. Whether how much you need to treat a cow, I don't know. Hopefully it would be across the different strains.
Great talk, loved it. I was curious about route of administration for this. I guess TB is a lung disease. Is it possible to have an inhaled treatment? Is it just not right for this patient population?
Well, I think, yes, a lot of the TB resides in the lungs, but and I think you saw in Kelly's talk, it hides away in very many places. So it isn't just a matter of, I think it's the acute phase is in there. I think there might be some bigger experts than me in the audience who might nod their heads, but I think it isn't just a matter of getting to the lungs. You do need to spread out and treat it in other places. Because usually it's a latent infection in most people. So I don't know, maybe statistically a third of us have it. And and it won't be in your lungs, it will be everywhere else. And that's where you need to get. So, inhaling could work for an acute one, but I'd imagine long term you need to get to other places.
Okay, I think we move on for the video feed. And if you join me thanking Rob again in the usual manner. Thank you. Okay, our next speaker is Jonathan Large. Jonathan received his undergraduate from the University of York in 1996 and remained there to study for a DPhil. He then moved to the University of Bristol for a postdoc with Tim Gallagher, and then he joined the Institute of Cancer Research as a medicinal chemist, working on a number of preclinically successful small molecule programs. In 2007, he joined the MRC technology, which I found out today was now renamed as LifeArc, where he's currently a senior scientist in the MedChem group. He's involved in a whole range of drug discovery projects, from antibody drug conjugates to small molecules. And today he's going to talk about potent and selective orally efficacious inhibitors of Plasmodium falciparum protein kinase G.
Thank you, Chris. Afternoon, everyone. Just to start by thanking the organisers as well for the chance to come and speak about this work today. This is going to be a much earlier stage story in a sense, and about a slightly different way of trying to tackle malaria than some of the things we've seen in trying to find potent and selective compounds to inhibit this Plasmodium kinase. Just ahead of that, another in the series of obligatory slides, because my employer changed their name over the summer. Having come from a background of doing tech transfer work and translating MRC science, particularly over the last 10 to 15 years, we've begun to work with a much broader range of collaborators, not just academics, but industrials, and not just here, but across the world. And having worked on humanizing Keytruda a while ago, we monetized part of that last year. and so became fully independent and with a new name in the spring of this year. Working collaboratively is very much at the heart of what we do in many cases with academics, and today is one of those. And we're going to try and take that further as we look to try and develop focus in these specific areas, though not exclusively. And we've also just announced significant new additional funding for early stage research work. So if you'd like to know more about that, do please come and talk to us. We'd love to discuss with you how we might be able to work together. And we do that mainly out of new labs in Stevenage, where many of our lab-based scientists now are. The skyline is not Cape Town, so I took the picture from as close to the building as possible. But on to today. I'll start with a little about the target, which was brought to us as a project proposal by David Baker from the London School of Hygiene and Tropical Medicine. And David had followed on from earlier work in other parasites and done a lot of work to validate this target in an in vitro malaria setting. And say something about the collaborative project we've since done together. But in talking about the MedChem, after showing you where we started, I'll only really touch on the compounds that for us really kind of move things on reasonably quickly. Before saying something about what happened when we took some initial looks in vivo. So we've seen this already today in other forms, but perhaps just a quick reminder that the life cycle of Plasmodium is complex, and it's in two distinct components in the human and mosquito, and it's this section here in the red blood cells that's responsible for the clinical symptoms, and that's the way that a lot of earlier anti-malarial treatments have worked. And as we've seen, there's a need in the malarial research community for new kinds of ways of treating malaria that act at various different stages of the life cycle. And this is where David's interest came, and when he came to us, he'd been interested in CGMP signaling in malaria for several years. And as you can see from the arrows, that appears to be important not just in the blood stages, but elsewhere as well. Of course, in humans, that signaling pathway in human cells, that drives an awful lot of different cellular processes, but there's a reason why we think it's targetable in malaria, which I'll come to. And one of those reasons is that there is only a single CGMP-dependent kinase in parasites, and that's PKG, though there are 3 human isoforms. And David, following on from others, have shown that it seems to be essential in the blood stages, and there's a growing body of evidence to suggest similar levels of importance elsewhere. And much of that earlier work was done making use of these biochemically quite active compounds whose origins came from work done at Merck Sharp and Dohme Animal Health, who were looking for inhibitors of PKG and Eimeria tenella, which is a parasite that causes an infection in chickens. But the key piece of info that David's made use of here is that PKG's got a small gatekeeper, and it has in tenella as well, and that's relatively uncommon, certainly in a malarial kinase. And by mutating it to a bigger one, you can confer sensitivity to the in vitro effects of compounds like these. And David's taken this one step further and generated a mutant parasite line, which has been very valuable in confirming some of the on-target effects of these compounds. And some of those in the blood stages are shown here. If you treat wild-type schizonts with these compounds and look for a percentage of red blood cell rings after 24 hours, what you see is a really dramatic reduction in that process when you treat with these compounds at roughly micromolar levels. But if you switch to the gatekeeper mutant schizont system, that process proceeds completely normally. And if you hone in on letting the schizonts rupture and look specifically at the process of merozoite reinvasion of new red blood cells, you see exactly the same pattern in the wild-type system as compared to the mutant system. And that's pretty important because it suggests that the primary target of these compounds in inhibiting these processes is PKG. And David's since gone on to do work showing that similar things happen when you use this system in transmission blocking contexts as well. And in collaboration with Andy Tobin's group in Leicester, proteomic type approaches have shown that over 100 different phosphorylation events are mediated by this enzyme in the blood stages in schizonts, and that there seems to be a significant link between this and calcium signaling pathways in mediation of some of these processes. So there's a kind of sense that it acts as some kind of signaling hub here. And among the many proteins the enzymes it phosphorylates is CDPK1, and that's something that we've also had an interest in an earlier collaborative program, which one of my colleagues, Tim Chapman, talked about here 4 years ago and has since published some of that work. But in terms of PKG, though, we've got a target with quite a lot of data I've not shown today, but which constitutes a really significant level of validation using this kind of chemical genetics, using those early 2 compounds. And so David applied for an MRC research grant, and we began to work on this collaboratively. And here's what we wanted to do. First of all, to find somewhere appropriate to start and identify whether we thought there were things that we could fix along the way, certainly in vitro, with an aim of certainly finding something potent and selective in vitro with properties, if we could, to have an early look at this mechanism in vivo. And that was really the ultimate goal here, was to try and challenge this mechanism, this specific kinase targeting mechanism in an in vivo biology setting. So we began by looking at those 2 early compounds. We decided not to screen at this stage, to look for more. And we actually picked the bicycle here as something that might, we thought, give us more options in terms of exploring SAR, and not least also on the basis of experience with similar bicyclic templates in the other kinase program. And as you can see, it's very biochemically active, but its whole cell activity here certainly needs some work. And though aspects of its in vitro ADME profile would appear to sit in reasonably good space, the mouse and human liver microsomal turnover numbers certainly need a little bit of attention as well. We measured its selectivity profile against, admittedly, a panel of human kinases, several hundredfold over its IC50. And you can see it's on the way to being a reasonably selective compound already. This is percent inhibition, but that there were a few kinases in particular that really stuck out above the tree line at that concentration. And so really key was trying to get those under control if we could in a compound that showed decent whole cell potency, and trying to keep hold of these as well in as good a place as we could as well. There were no crystal structures of parasite PKGs at this stage, so we built a homology model based on Gondii CDPK1, I think, where the homology was highest. And docking with this compound in suggested several areas of early work for us to take a look at. One was to confirm the optimum hinge bind, and others were to sort of look at lipophilicity control by seeing how far, if at all, we could truncate this group that sticks into the selectivity pocket, or perhaps by working on the core. And we also saw a chance to grow the aminopyrimidine out towards the pocket entrance a little, possibly instead of or as well as looking at replacing this rather metabolically labile-looking basic group on the core. I've just labelled these 2 positions particularly as what we thought might be good opportunities to add in small lipophilic groups if we could, and I'll say more about what happened there later. But say something briefly about the early SAR. We found, through not having to make actually very many compounds at all, that the original aminopyrimidine motif seemed to be optimal in most of the things we subsequently made. And then we turned to look at that basic group appended to the core, and this was done by Ella Smiljanich-Hurley, who's here. And she found that you could alter that group reasonably easily and in a variety of cyclic or linear types to get much better control of the in vitro ADME properties. Some of those compounds had really quite nice in vitro profiles. In the end, though, after other pieces of work, we came back to the original group because we found that it was metabolically stable, just about enough if the rest of the profile fit the bill. And when you move that basic group from on the core onto an extended aminopyrimidine group, Particularly when you link it by aryls, you see a really big cell potency boost, and I'll mention that. We did look at truncating this 4-fluorophenyl down a little bit, and we took that really as far as we could. Although some of those compounds did show reasonable levels of in vitro potency, as you might imagine, we couldn't really pair it up with a selectivity profile to match. Well, I'm not going to talk about monocyclic templates today. We did some work there, but in the bicyclic core sets, we did try looking at adding nitrogen atoms and one or two other things, and in some cases that gave us access to a little bit more structural novelty, but particularly solubility, as we've already heard today, actually was a particular problem with some of those. So a good chance to say that some of the early work did give us potent analogues in vitro, one or two of which were just about good enough to look early in vivo. But what I want to do now is just focus on one or two key things which moved things on for us fairly quickly. And the first one was this, that if you combine the basic group on the core with a larger group on the aminopyrimidine, you get a really big cell potency boost. This was one of actually the first compounds we made that was sub 100 nanomolar EC50, paired up with a reasonably encouraging looking in vitro profile as far as it went. And then we introduced that little methyl group on the core, as I showed you in the homology model, and this compound was first made by a placement student, Mary Weldon, who's also here. And she found that by doing that, you got another boost in cell potency against the parasite down to 25 nanomolar EC50. And it was always that particular regioisomer here that gave us the biggest cell jump. When you put it up here, maybe not so much. And though it obviously is a liability for human microsomes in this case, it wasn't always, in fact, not actually too often. And we tried a lot of things to change this linker into something a lot less lipophilic. And in doing so, we managed to get control of the properties a little bit, but we could never really match the headline potency of that compound in any of those. But we did see in this program a good translation from biochemistry to cell assay across a number of different kinds of aminopyrimidine group. But what was starting to become very clear was that by using larger aminopyrimidines, which are in the blue, we could make very active compounds, very cell-active compounds, but the juggling of properties was becoming, in many of those, more difficult, even though quite a lot of them had fairly decent in vitro ADME profiles. So we had to consider how to get around that. And one of the things we went to look at, again, actually, was the selectivity pocket, where the model suggested that there was a chance to pick up specific additional interactions in that area, and that if we designed in for that, we might make gains. And after, I think, first trying a sulfone, which is something we've already seen today, which is often used as a less lipophilic replacement for a 4-aryl analog with more lipophilic groups in the 4 position, we came first to the sulfonamide, and then fairly quickly afterwards, though it took some synthesizing, to the fluorosulfonamide. And you can see that we're back in a pretty good potency space against both the enzyme and the parasite, and that this is now aligned to a much more encouraging in vitro ADME profile, though we've lost quite a lot of the passive permeability, as we often did in the aminopyrimidines where there was no substituent there. And so that compound had some advantages for us, and we did the core methyl trick again in this position and saw once again that cell boost down to sub 50 nanomolar EC50 against the parasite. So getting quite interesting again. And then the project grant funding ran out. So we had to decide what to do, and our sense of curiosity, which there's nothing wrong with, got the better of us just for a little while longer, and we made a couple of compounds to tidy things up. And one of the last ones we made was this one, which kind of combined lots of what I've talked about with a smaller aminopyrimidine group here. We were trying as best we could to keep hold of that molecular size. And although it's very biochemically active, just to highlight how cell active it is, this was kind of quite surprising. We'd not seen anything like this before. but single-digit nanomolar EC90, which at the time we made it we thought one of the more active cell compounds, that certainly one that was targeted to a malarial kinase. And for comparison, the two known anti-malarials, though they obviously work by different means in the same assay. And we looked straight away for how we were looking off target, and using the gatekeeper mutant systems in both biochemistry and against the parasite. And I think the key thing to take from this is that the differential between cell EC50 and mutant cell wild-type enzyme EC50 and mutant cell EC50 is over 1,000-fold, and that was the biggest difference we'd actually seen throughout the entire program. So by no means a sense of total selectivity, but certainly a suggestion that we're looking on target, and that any secondary targets we might inhibit would only be so at fairly high compound concentrations. A little bit more in vitro detail. We're pretty happy with where its LLE sat using this metric, aided certainly by that very high cell activity. Passive permeability back in, because we've blocked off one of the NHs on the aminopyrimidine, we think. No sign of in vitro cytotox. The log D is creeping up, as is the log P a little bit, and you can see that reflected, I think, to some degree in the microsomal turnover, which may be in mouse slightly better than where we started. But allied to that level of cell potency, we're reasonably happy with that. We measured its selectivity profile against the human kinase panel at several hundred-fold over the biochemical IC50 again here. And you can see this is percent inhibition, but the scale is now much more truncated. So this is looking like a much more selective compound. The three you saw before are essentially back down in the noise. But for completeness, we took the one that was sticking up most, MLK3, and had its biochemical IC50 measured, and the window is greater than 600-fold there. So what we thought was a really selective compound, at least against the human kinase panel. And Ray Huey's group at SGC was able to co-crystallize this into Vivax because falciparum didn't give us suitable crystallography, though the homology among the kinase domains there is very high, so we're happy that it's a good surrogate. And you can see the confirmation of the new interactions in the DFG selectivity pocket area there. And though you can't see it on this version, this little aminopyrimidine group sits really snugly into a hydrophobic binding cleft on the way out to the pocket. And this has just been published. So we felt a pretty interesting compound, and the best we could really find at this stage, having done that work on that chemotype. So we decided to look in vivo, and the first protocol was Bergii. I won't go through this in too much detail because it has been mentioned briefly before today. But it's a 4-day test, and one of the key things to remember here is that this is Bergii, not falciparum, so rodent rather than human. And the way the assay works is that you take blood on a day after finishing your treatment with your compound and look for parasitemia, usually by fax. And your results come back as a percentage reduction in blood stage parasites relative to your untreated mice. And it's often positively controlled by chloroquine, which at this dose effectively wipes out parasitemia in this model. And here's what we found. We had problems with solubility as well, so we had to dose this as a salt. But if you look at 25 mg a kg twice a day over the course of this model and compare where you started, the starting compound already shows an interesting level of blood parasites reduction, but where we got to doesn't show you any more. And a couple of things we thought of alongside that was to consider the plasma analysis, where we'd given the compound to a non-infected group of mice at the same time. And although it seemed to be reasonably well absorbed early, that seemed to drop away fairly quickly to still above the EC90, but only after 4 hours. So that was one thing. But we also thought that Bergii is an asynchronous model, and that means that the parasites develop at all different stages of the life cycle, as you might expect. And we wondered if we could use a different model to focus the compound dosing on that fairly narrow window of PKG activity in the blood stages. And we did that by moving to Shabodi, which is synchronized, and another rodent model. And to make use of that most easily, you have to reverse the mouse day-night sleep cycle 2 weeks beforehand. And if you do that, then schizogony is then predicted to start in the middle of the day, not the middle of the night, which is helpful. And if you give a single dose of this compound to one group just prior to that time point, what we decided to do was give a second group an additional dose of the same size, just to try to make sure we had enough on board to cover that activity window. And here's what you see, that there's no real improvement on single dosing, but when you give another dose to try to cover that window, you do see a big improvement in the reduction in blood stage parasites, which was quite encouraging. And we looked at plasma here again, and kind of same story, but with probably slightly better absorption, even better absorption. This number doesn't take into account plasma protein binding, but it's the actual EC90 from the falciparum in vitro assay. But again, out to 4 hours, it's still pretty well above that, but it's dropping away fairly quickly. But no overt signs of tox in this or Bergii either. So we were able to look at this compound finally in the skid mouse model, which, as you've heard, is GSK's developed way of looking at falciparum instead of the rodent species in a mouse. But to do that, you have to immunocompromise the mouse so that it'll accept a suitable strain of falciparum as part of the injected red blood cells. And if you do that, and you dose at slightly bigger doses here, we wanted to try and push this to see how far we could test the mechanism. And you see that certainly particularly at the higher of these two doses, over the course of that 4-day treatment, you're able to completely ablate parasitemia below the levels of detection, which was really good news for the mechanism in the blood stages we felt. And Tres Cantos also looked for where the parasites are. After one parasite cycle, the blood stages in falciparum are 2 days relative to 1 day in Bergii. And if you look by FACS analysis, they're all pretty much all at the late Schizont stage, which again is suggestive of on-target activity against PKG there. We did actually look at whole blood levels after one dose of each level, and you can see here that we seem to get better exposure as compared to previous models, which was something we'd also seen in the earlier kinase program, but particularly at the higher dose, it seems to be around a lot longer in vivo in this setting, which we certainly feel that's one thing that contributed to seeing a better efficacy in this model as compared to the other ones. But just to finish, referring to something that Kelly and others have spoken about, and this is the first piece of data about taking this compound and using it to unravel some of the in vitro biology around the life cycle of the parasite. And this is about transmission blocking, whereby you infect gametocytes with the compound and then feed those gametocytes to groups of mosquitoes, and a week later look for oocyst numbers. And if you do that with this compound, you see a really nice active IC50 for the reduction in infection intensity in that assay. And that's kind of what we think is almost as important about this compound as the blood stages, that it's starting to be used to validate this mechanism in other areas of the life cycle. So just to sum up about that bicyclic series which we've worked on, where the best examples we found had very high levels of cell potency matched with really good levels of selectivity against the one malarial kinase we wanted to target. And the ADME we just about managed to keep hold of enough to go in vivo with this. And you saw the way we used the synchronous model to look for higher efficacy by looking at that fairly narrow window of PKG activity window in the blood stages. And that by looking in the SCID model, we were able to clear parasites with an on-target compound and giving us a degree of POC for that mechanism in the blood stage. But But we finished there, and much of this work in other areas of the life cycle is still ongoing outside of our project. But the activity of PKG is now being examined using that compound. And certainly if you could improve the PK a little bit further, we think that this work points to the value of this mechanism, particularly as part of combination treatments. And to finish by acknowledging the project team, 3 people in particular. David brought the project to us as a target proposal, and his group at the London School of Hygiene. Simon was my manager at the time, and he led the MedChem programme. And Katie's our head of biology, and she managed the project. And just also to thank our collaborators. These guys on the slide generated data with us and gave us great input. There were lots of others whose work I didn't mention today. And it was a research grant given to us by the MRC. And thanks very much to you for listening as well. Thank you.
Very, very nice talk. Thank you. Any questions?
Thanks, nice talk. So maybe it's too early of a compound to worry about this, but did you look for, or were you concerned about potential metabolite of cyclopropyl carboxylic acid?
We didn't do any meta-ID on this because it was a bit late in the day. But yes, I think there were certain other combinations that we didn't quite get to, where we looked a little bit better in terms of metabolism earlier in the SAR, but we just kind of ran out of time and couldn't really go back and make those. But yes, I think you're right. Yeah.
Yeah, really nice talk, thanks. We've seen several different anti-malarial programs with different structural classes, different mechanisms of action. Is the eventual goal then to combine drugs of different mechanism of action and then shorten the cure time?
I think you're right, yes. I think I didn't mention kill time because we've only got a fairly limited amount of data on rate of kill with this series, but it's something that's often used to prioritize new mechanisms. This one, I think you would probably expect to be slower acting, and initial data we've seen supports that in vitro at least. But I think after you might expect, although you might expect a delayed onset of action because of a mechanism like this, we think that this will probably sit best either as part of a combination or perhaps even prophylactically, because there is a suggestion of CGMP activity in the late liver stages as well. But I think combinations is most likely for this. Yes, I do, yeah.
Thank you.
You mentioned at the start you had this selectivity problem with P38 and other kinases. Did you actually actively design compound not to be active against them, or was it at the end of your project you realized you didn't have the activity anymore?
Yeah, we didn't deliberately design against those, partly because we used the PPU unit in Dundee to do our kinase screening, and actually those 80 kinases weren't exactly the same. I should have said that, but the key ones that you saw being really highly inhibited at that concentration were still there, but the makeup of that kinase panel does change slightly from time to time. But no, we didn't design specifically against those.
Thank you.
Okay, if there are no further questions, I think we should thank Jonathan in the usual manner. Thanks very much. Final speaker in this session is Charles Moseby of the DNDi. Prior to joining the DNDi, he spent 19 years at Pfizer Worldwide Research and Development in Sandwich. During that time, he developed or was involved in a number of projects across many disease areas, target classes, and different medicinal chemistry strategies. And he was involved from target selection right through to clinical delivery. 5 of those molecules have entered phase 1 and 2 have entered proof of concept in phase 2b. At the DNDi, He's led a number of multidisciplinary teams working on a whole variety of neglected tropical diseases, and has been a key player in developing multiple consortia to work in various different areas. Today, he's going to talk about the first disclosure of new oral development candidate for the treatment of visceral and cutaneous leishmaniasis, and he's also going to give us a roundup at the end of the day. Over to you.
Thanks, Chris, and I just add my thanks to the other speakers this afternoon. Really appreciate the opportunity provided by the organisers to shine the light on neglected diseases and talk about some projects that maybe don't make it onto the agenda in meetings like this very often. So it's a real pleasure to have the opportunity today. I'd like to tell you a little bit, first of all, about DNDi, because probably not many people have heard of us or what we do. So a brief introduction there. Kelly gave a nice introduction for Leishmaniasis. I'd like to add a few thoughts of my own, a bit more food for thought about some of the challenges and the particular problems we face in trying to discover new drugs there. And then show you how we operate and show you one of our programs where we're trying to find a new candidate to provide an opportunity to explore further in the clinic in patients. So DNDi, Drugs for Neglected Diseases Initiative. It's a bit of a mouthful, so DNDi. We were born in 2003 and really at the behest of a number of our founding partners, recognising the needs of patients that weren't met by the traditional incentive models and the traditional pharmaceutical industry and the focus of many researchers around the globe. So for patients suffering from neglected diseases, the ones that Kelly showed you, but also patients that suffer from diseases which and their needs aren't met by the existing treatments, we're really trying to move the bar and find new treatments, make them available for those patients, and provide access to the treatments for everybody. So we're a virtual R&D organisation, but we also passionate, advocate really hard to change the research environment and to increase access to medicines for all, and to try and find new medicines where they don't exist. And we're also very keen to work with our partners, particularly in endemic countries, to increase the capacity to do an R&D for diseases in the regions in which they're really relevant. So you can see here some diseases we've been working on, a trio of kinetoplastid diseases. So these are caused by protozoal single-cell parasites, so sleeping sickness, Chagas disease and Leishmaniasis, but also diseases caused by worms, so onchocerciasis, lymphatic filariasis, deep-seated fungal infections such as mycetoma, but also some diseases like pediatric HIV, where very young children and babies aren't really served by the medications that have been developed for adults, and so coming up with better combinations, better formulations that are really adapted to meet the needs of those special populations is something we've been looking at. And finally, at the end, I'll say a few things about hepatitis C. It's clearly not neglected, but I would argue that not all the patients that need the medicines are getting them, and there are things that we can do to help there. And finally, in the last 18 months or so, DNDi has been incubating and setting up a new organisation, largely at the request of the WHO and other actors in this field, called GARD-P. So this is the Global Antibiotic Research and Development Partnership, recognising the huge threat to humanity of drug-resistant bacteria and fungi, and looking to see how we can contribute in this space. Clearly, it's a busy space. A lot of other people are thinking about this too, but really taking a patient's needs and global health view about how can we fill in the gaps and complement what other people are doing and bring people together in this space. So plenty for us to do here. We're a young organisation. I would say in the first 13, 14 years, we've been relatively successful. We've managed to bring 7 new treatments forward. These are largely combinations, reformulations, paediatric formulations, for example, but treatments that have been brought forward relatively quickly and are helping patients quickly. They're not using necessarily the very best medicines, 21st century medicines. They're using what's available. They're saving lives and they're making a big difference. And this will always be our first approach. How can we most quickly help patients? But sometimes there aren't good drugs. There aren't things that we can combine or reformulate or continue the development. And then we need to do research and development. And I'll tell you more about that in a minute. This wide disease portfolio means we've got a lot of projects, a lot of ongoing clinical trials. We're a virtual organisation. We have no laboratories of our own. So everything we do is by partnership, by collaboration. We have a huge number of partnerships, more than 160 partnerships around the globe with
universities, research institutes, biotechs, large pharma, ministries of health, governments, whoever we can bring together who's got an interest in helping us tackle these problems. So I would say a uniquely collaborative environment and really everybody trying to help in this space rather than compete. DNDIs itself is a modest organisation, around 160 staff. A little less than half of those are in Geneva. The rest are distributed in regional offices, particularly in endemic countries where we're running clinical trials. And we directly employ in the partner organisations that we work with something like 5 times that many, so probably another 700 people. A critical pillar of what we do is rooted in the clinical trial platforms and the disease platforms that we have. So for sleeping sickness, for example, we have a platform of investigators and key actors in Africa that are really working together to help us understand the needs of patients, but also to advocate for change, to run clinical trials, and to help us in our mission to bring new treatments and make them available to everybody. So those disease platforms are really special. They're working in incredibly difficult situations. We're running clinical trials in sleeping sickness in the Democratic Republic of Congo. We're running trials in visceral leishmaniasis in Sudan. We're treating patients with Chagas disease and leishmaniasis in Colombia and Peru. These aren't easy environments necessarily, and not places where traditional pharma companies would find it very easy to operate. So it's really, really important for us to have those roots and those connections to the patients and the folks that are treating them. So, quick snapshot of our portfolio. It's quite busy. I've told you about these treatments over here. This is where we've finished the job. These are making a difference, but they're not enough. For some of the diseases, I'll tell you later a little about sleeping sickness. We're hoping we're reaching some new treatments that are really going to change the game. In other places, we're using existing treatments. We're doing combination studies in HIV. We're hoping that we can find those properly adapted, patient-adapted formulations that'll make a difference. In other diseases, such as Chagas disease, Leishmaniasis, there just aren't good drugs. That even however hard you try, you can't find combinations that work for everybody, and you need to do drug discovery. And so it's great for me to see a number of preclinical candidates beginning their development stage, and we hope that some of those will go on to become future drugs and future combinations for treating patients. And it's one of those I'm going to tell you a bit about today. So Kelly introduced Leishmaniasis. I'm not going to add too much, but just to remind you, it's an intracellular parasite. So after being bitten by a sandfly, this parasite will enter your cells, particularly your macrophages and other immune cells, and it doesn't just go into the cell, but then it hides out in the parasitophorous vacuole inside the macrophage. So for a drug to reach it, it's got to be an oral drug, it's got to be absorbed, distributed, get into a macrophage, so through some membranes, and then into a parasitophorous vacuole, where the pH is probably around 4 to 5, traverse that pH gradient, and then get into and kill the parasite. So it's a difficult location for a drug to reach, and the parasites are already well adapted and are good at evading the immune system and are particularly difficult to kill. So we've got some challenges. This disease is, it's prevalent. You saw it in Kelly's charts. There's more than 1 million cases a year. You've heard about a range of different manifestations from visceral leishmaniasis that I'll focus on today. More than 20 to 30,000 deaths a year from visceral leishmaniasis. It occurs in outbreaks. It's a disease of poverty, malnutrition, and war. So in countries like Sudan, in places like Syria at the moment, there are outbreaks because the environment's right for the parasite. So these numbers go up and down, but they don't go away. A large number of people live in regions where these diseases are endemic and are at risk. So we'll keep seeing these diseases come back unless we really work hard to eliminate them, come up with good treatments and combinations that we can use to treat patients, reduce transmission, and really work towards elimination. So I've called this slide the good, the bad, and the ugly. This is the current standard of care. These are drugs from the Dark Ages. They contain antimony. This was the standard of care. It still is the standard of care in some regions. They're drugs that do work for some patients, but they bring significant toxicities. They're really unpleasant to receive. I don't think anyone here would really like 28 days of infusions with a toxic, painful drug that causes a number of side effects and may not cure you. Even in combination to reduce the treatment and make it more tolerable, they're still not good enough. Leishmaniasis, again, as Kelly told you, spans particularly the southern hemisphere, so the Indian subcontinent, Africa, Latin America, also the Mediterranean basin. It's not just in Syria and some other North African regions, but also in Mediterranean basin, Spain and Italy, for example. So this disease is all around, and the response to treatments isn't the same. So drugs that work in India don't work well in Africa and Latin America. We don't understand fully why, but probably it's a combination of differences in parasite and host, and we need to find new drugs that work for all of the patients in all of the regions. So, you've got these toxic heavy metals, you've got complex natural products which also require repeated infusions or injections. They're not easy to use. This one, amphotericin B, as a liposomal formulation, requires a cold chain. Cold chain in countries where it's 30, 40 degrees in remote settings, not easy. Finally, there's one here that's oral, hooray, but unfortunately this one is teratogenic. So they've all got problems, and however you try to combine them, there aren't great options here, and we really need to find some new compounds that we can combine and really come up with a 21st century medicine that these patients deserve. So working with our clinical trial platform and our disease experts, we've really thought hard about what is it that we need in an ideal or at least an acceptable new treatment. And really we're looking for a drug that will tackle all of the species of Leishmania. So visceral leishmaniasis is caused by two species, Leishmania donovani and Leishmania infantum, but cutaneous leishmaniasis is caused by 20 more species. So we would like a drug that tackles all of those species, in all the regions, in all the patients, whether they're relatively healthy as a patient who's probably malnourished and poor can be, but also those that have got HIV co-infection and other reasons for a suppressed immune system. We want good efficacy in all those regions. We don't want to have to adapt the treatment for the country or the particular region of a country. We want drugs that are going to be active. There are some resistant parasites to some of the existing treatments. We want drugs that are going to be active against those so we can try and protect ourselves against emerging resistance. We don't want drugs that are difficult to use, that require difficult monitoring for patients. Again, you've heard about the setting. It's not easy to have complex follow-up of patients. They may not even be in a healthcare setting where there's any access to that sort of service. We want to combine them probably. They may be on other therapies, especially if they've got HIV as well. So drugs that have not going to bring drug-drug interaction issues and understandable clearance would be helpful. Ideally oral, it would be simplest. There was a discussion earlier about would injectable be okay? Well, yeah, if it was one shot, if it was a simple one shot, it didn't require a cold chain, etc. That might be acceptable too. But really, we've tried to focus on new oral therapies. We think that'll be easiest and best. Got to be stable. It's going to be hot, humid, difficult conditions. It's probably going to be sitting on the shelf in pharmacies in some remote situations. Got to have great pharmaceutical properties. And at the end of it, we want to make it accessible, so it's got to be cheap. So let's not make it too complicated, and let's try and make sure that we come up with something that's fit for purpose. So that brings me to this particular project. This is a very collaborative project. Back in 2009 or 10, BNDI signed an agreement with Pfizer to screen some of the Pfizer corporate collection, looking for new leads to begin projects for leishmaniasis and other kinetoplastid diseases. We've gone on, as I'll show you, to find a series that was interesting, and then we managed to engage some help from Takeda in Japan, who've been fantastic as a partner, really helping us to do the lead optimization project. We were able to do that because the GHIP fund in Japan was also prepared to give us some generous financial support, and working with long-standing partners of the NDI, the real disease experts, the London School of Hygiene and Tropical Medicine, the University of Antwerp. This is where the parasitology experts live and have really great models that help to guide the medicinal chemists. Lots of the heavy lifting's been done by CROs, particularly WuXi in China doing chemistry and DMPK. And a lot of the medicinal chemistry and project management and leaderships come from consultants in the UK at Sandexis. I can't thank this team enough. So I showed you a target product profile. That's great. As discovery scientists, we need to translate that back into a set of laboratory objectives or a target candidate profile. And that's what we've tried to do here. We're looking for compounds that have got good activity in vitro against drug-sensitive and drug-resistant strains of parasite, that work in animal models. I hesitate to use the word model because Leishmaniasis in animals is not the same as it is in human. The immune response is different, but we have mouse and hamster models where we can inoculate, generate an experimental infection and look at the effect of drug on parasite load in liver, spleen, and bone marrow, which are the key target organs in humans as well. We'd like to see a very large reduction in the parasite load, ideally getting rid of all of those parasites after a short course treatment. It's going to need to be safe, so we want to just avoid difficult molecules early. If we've got signals that are going to make development difficult and safety an issue, we should avoid those. We're prepared to take some risks. We're thinking about a short course treatment for a life-threatening indication where we could cure you and you could then have a long and happy life. So perhaps the safety requirements for a short course treatment might not be quite as demanding as they are for a long course TB treatment or a long course cancer treatment. So we're pragmatic and we'll try and take compounds forward if we think they're safe enough to develop. We need to be able to synthesize them, formulate them, and get them into the patients in a reasonable way, and so we need to think about the formulation development properties. And there are limits to what you can do. So, this is definitely the upper end of where we'd go in terms of dose, but we're pragmatic, so high doses for anti-infectives is not unusual. You do need to kill the parasites, so you may need quite large doses, and we're prepared to try that. So I've told you about some of the partners. Medicinal chemistry design and synthesis, or design by Sandexis and Takeda. The chemistry is being done at WuXi these days. In the past, we've had a lot of help from some other CROs, such as Synexis and Itemba in South Africa. And the parasitology has been run in these labs. Good to have a couple of labs with different models and different expertise, different sets of strains. It's been really, really good working with different labs. And reproducing the results in different labs, I think, is also good, as we've heard in some of the presentations today. So very much a global team, very typical for our projects. We designed a screening cascade, trying to spot the winners early and weed out the chaff as quickly as we could. So design and synthesis, and then quickly into a very valuable tool. So this is a phenotypic whole cell assay, looking at the ability of a compound to kill the parasites in those parasitophorous vacuoles inside macrophages, inside primary cells or in cell lines. So that tells us a lot about the journey the compound has to take to reach the parasite. It's helping us to de-risk some of that permeability, pH gradient, and so forth, issues that I described earlier. So if we get a compound that works in this assay, that's good. It's really tough to find these in HTS. The higher throughput screening hit rates are less than 0.01% because of all of those issues, and it's tough to find compounds that kill the parasite without killing the host. So we also look at cytotoxicity in primary cells and in a human cell line as well, just to get an early read on whether we've got a parasite-specific effect. Compounds that look interesting there, we'll go on and do very standard in vitro ADME, looking at oral exposure in hamster or mouse to decide whether we've got enough drug on board to make it worth testing in a disease model, and to see whether we can knock down the parasite in vivo. Compounds that look good, we'll go on and do more PK assessment and try and make human predictions and think more about the safety. Obviously, we go around this cycle lots of times trying to find a good compound, and you can see what the different partners are doing in this. I mentioned the in vitro assay. I think this is it's a very powerful tool for us. It's not a simple tool. It's difficult. It requires a long incubation, so the turnaround isn't very fast. We can't do cycles of MedChem every week. It takes a bit longer, particularly when we're working with a global consortium like this. We do most of our primary work using Leishmania infantum, which is one of the species of Leishmania that causes visceral Leishmaniasis, that acute systemic life-threatening form of Leishmaniasis. The other species is Leishmania donovani. The good news is that our series, by and large, hit both parasites species with similar activity, but it's important to check and make sure we haven't developed something that's too specific. So where did we start? Well, we tested around 100,000 compounds from Pfizer's representative deck, and we found really just one hit that was new and looked as though we could go somewhere with it. It was a unique one. There really weren't any close analogues in the Pfizer deck. There were similar compounds, but they lacked significant chunks of this molecule or had significant differences. It was quite a weak hit. I still reflect on how lucky we were to find this one. Moderate activity, not very metabolically stable. It would have been easy to walk away. Happily, we didn't, and we tried hard to make some analogues because hits are really tough to come by, and so we tried very hard to turn this into an interesting series. We really struggled with the amide series to improve metabolic stability. We could get better potency, but we needed to maintain a certain degree of lipophilicity. Again, the story we've heard this week. So it's tough to find potent compounds with a log P of less than 2, but it was very hard to find stable amides, maybe not too surprising, wherever we were working within the log P range. Happily, we made a switch. We nearly stopped many times, but we had a break. We swapped from an amide to a urea, and we found this moved us to much better space. We found we could get compounds now with really very respectable metabolic stability in human liver microsomes, and also as long as we stayed in a lipophilicity region of around 2 to 3.5, where we felt we could get metabolic stability, we could still get potency down to or less than 1 micromolar. 1 micromolar may not sound that active, but again, it's this complicated phenotypic assay in the presence of proteins, and so actually getting a potency down towards 1 micromolar is really good, and that's the range that some of the existing drugs are in. If we can get less than 1 micromolar, that's pretty rare and very promising indeed. So, we got some encouragement. We found a series where we think we can combine some properties, and we've got some guidance on what space we should be working in for physical properties. We made a number of analogues, and we published a couple of years ago the initial progress here, and this is what got us really excited. We managed to go from this hit to a few compounds, such as this one shown here, where we're able to combine moderately good potency with sufficient in vitro ADME to get exposure in vivo, and so by oral dosing, we were able to get an in vivo proof of concept. We could knock down the parasite level in liver, spleen, and bone marrow by more than 90%. Against Leishmania infantum infection in hamsters. That's really rare. There's not too many series that do that. So we were excited and keen to move forward. And this is the point when Takeda got in to help us, really helping us with the design and the advice and expertise of a company on board really helps with a project like this. So just to look at this lead a little bit more, you can see that here's the potency and selectivity. We're not hitting the host cell for this assay is a peritoneal mouse macrophage, and so we're right at the top of that assay. We've got a selective action on the parasite. Moderate kind of metabolic stability, perhaps not great kinetic solubility again, perhaps not too surprising, but the good news was that after oral dosing of a simple formulation, we got this knockdown of the parasites. And when we had a look at the PK in hamsters and looked at the drug exposure in plasma as a surrogate for what might be going on inside a macrophage, we could see that the peaks of the concentration were at least going above the free IC50 from the in vitro assay. So this is not a PK/PD model, but it was giving us some confidence that there was enough drug around to explain what we were seeing. And this in vivo proof of concept really encouraged us to pile in and do some more. So we've made a lot more compounds in this series over the last 3 years. It's proved difficult. There's a summary here of many of the things we've tried, but in general, it's very difficult to modify the left-hand side of the molecule without losing all the activity. Just a few small changes are tolerated, but not really giving us any improvement in properties. Happily, on the right-hand side of the urea here, really quite open to modification, and it's given us the opportunity to modulate potency, physical properties, and to really try and improve the properties of the molecule and look for compounds with good in vivo profiles. So it's a quick summary of a lot of work there. We've learned more about the property space, and again, you can see here potency on the y-axis, lipophilicity on the x-axis, really focusing in on that sweet spot in that range of 2 to 3.5, which for neutral molecules seems to be a reasonable place if you're going to try and get sufficient metabolic stability. And that's allowed us to go on and pick out the best compounds and profile them further. Which brings me to our first generation lead compounds. So we had a small number of compounds typified by this one here, which I'll call DNDI 1047, this parachlorophenoxypyrrolidine. Really good potency in vitro. As I mentioned, getting less than 1 micromolar in these assays is tough. So this sort of potency really makes us sit up and take notice. And I'll show you in a minute, it's not just against the species that cause visceral leishmaniasis, but also against those that cause cutaneous leishmaniasis. So really getting more excited. Good selectivity, and the physical properties aren't bad, so we see good permeability in an MDR1 and MDCK assay with no evidence of efflux. So good permeability. And from at this stage, the limited off-target profiling we'd done showed that the compounds were really quite selective. Surprisingly enough to me, very little activity against any kinases, and some in a broader panel, just some weak activity, or activity against the dopamine transporter and some weak activity against alpha-1A receptor. Clean in genotox assays, and so we're feeling quite optimistic. I'll show you a bit more about the in vivo data in a moment, but this is even better than our earlier compounds now, so we're really getting up to the top of the assay, seeing very high levels of parasite reduction, both in hamster and in mouse, in 2 different laboratories, with Leishmania infantum and Leishmania donovani. So really strong validation that whatever we're doing to the parasite is doing it to all the parasites and in different environments. And furthermore, I'll show you some CL data in a minute. So in a different type of model where the parasite's in the skin, where we've got unprecedented data and really evidence that we're getting rid of all of the parasites. Compound pharmacokinetics is being looked at more in rat, and it's relatively low clearance, moderate bioavailability, and looking at the exposure that we require in animal models to achieve a good knockdown of parasites, we can predict what sort of dose we might need in humans. And it looks like a reasonably modest dose, 5 to 10 mg per kg twice a day could do the job. 1 or 2 flags for us at the moment. So the compound, it's permeable, it gets into the CNS. We don't know the mechanism of action. It works in a phenotypic assay. We don't think there are parasites in the brain, and so having high drug concentrations of unknown mechanism in the brain might not be a great thing. And also we discovered that there was some evidence in vivo of trapping by glutathione, so suggestion of some reactive metabolite formation. So here's just a little bit more of that data. This is the in vitro data for the species that cause visceral leishmaniasis, a bigger panel looking at a number of the species that cause cutaneous leishmaniasis, and you can see we're retaining good activity across the species here, which is great. And interestingly, really not much activity against quite closely related kinetoplastid parasites, Trypanosoma cruzi that causes Chagas disease, and Trypanosoma brucei that causes sleeping sickness. So we have an interesting series, and it's one of the things that encourages that perhaps we found a good target for whatever it might be for these compounds, is that we're seeing this specific action. In the in vivo data I told you about, you can look at, particularly in hamsters, you can look at different tissues. So we can look at liver, spleen, and bone marrow, and we can see a really good knockdown of parasitemia. Even in the bone marrow, which is much more difficult to assess, we can see a good knockdown of parasite level. For us, this meets our target candidate profile. We're happy that we've got the efficacy that we're after. And we've got a number of other compounds that do this as well. But potency is not everything. In vivo efficacy is great, but it's not everything. Finally, I mentioned a model of cutaneous leishmaniasis. So in this model, the mice are inoculated with parasites under the skin at the base of the tail, and a lesion forms in the skin. If untreated, that lesion will grow, and so the lesion size in square millimeters will continue to grow during the experiment. With the standard of care, so amphotericin B is a liposomal formulation, ambisome, is pretty much static, so that's the best treatment available, then it doesn't really make too much difference. The lesion's still there. What's exciting for us is that with a dose response, our compound is knocking down the size of that lesion and it's disappearing. And after 30 days, there's no parasites there by qPCR, and the lab where this was conducted with Simon Croft at London School of Hygiene and Tropical Medicine said they hadn't seen data like this before. It's really unprecedented, and they were as excited as we were that we've got a new class of compounds with great potential for VL, but also for cutaneous leishmaniasis, CL. So coming back to the rest of the profile, here's the PK data we mentioned. Low clearance, moderate bioavailability. We profiled it quite extensively. And made a human PK prediction and a dose prediction based on this efficacious AUC from the hamster model. So quite promising, but let's come back to some of the flags. So negative in the gene tox assays, which is great. We were seeing some, reasonably significant inhibition of the dopamine transporter. Some signals on the alpha-1A receptor. I think I was more worried at the time about reactive metabolites. They're difficult things to quantify and to really understand downstream. Overall, the safety looked reasonably encouraging. We could continue, but we were more inclined to go looking for a compound where we'd address some of these risks and to really come up with a high-quality compound that we'd have more confidence progressing into development. Here's just some of the meta-ID work that was done in vivo with this compound, and you can see evidence of trapping by glutathione. Particularly, and we believe what's happening here is oxidation of the aminopyrrosole, leading to a reactive species that can get trapped out by glutathione or other nucleophiles. And actually, as we were doing this work, a nice paper came out from a group at CDCO in Australia looking at aminopyrrosoles and identifying this flag. So another risk for us and something to try and address. So in our strategy from this point, we were looking for, to build on these first generation leads, to really try and optimize the profiles, mitigate some of those risks, and come up with some compounds that would be better potential development candidates. Having said that, our hands weren't exactly tied, but we just couldn't do very much on the left-hand side of the molecule. Really critical to retain good activity, difficult to modify this place. Happily, we found at this position on the pyrrosole, the 4 position, we could put small lipophilic substituents or chlorine in this position. The good thing is that shuts down the oxidative metabolism, the formation of the reactive metabolite. So particularly a cyclopropyl group in this position seems to give good activity and blocks that pathway that can lead to reactive metabolites. So that was something we were keen to explore. And we hope that further modification of the right-hand side would allow us to address those off-target activities and also think about maybe trying to keep the compound out of the brain. So a well-precedented mechanism for doing that is making your compound a PGP substrate so that it's effluxed faster out of the brain than it can get in. That works very well for H1 antagonists, for example. So that's a strategy we felt we might be able to exploit if we could understand and optimize that activity. So thinking about this, what is it that makes a compound a PGP substrate? Well, you can be lucky, you can screen, but also I think you can use models, you can use physical properties. So we were thinking, well, probably polar surface area is important. There are some models, such as one we were using in StarTrop. And we found that if we designed and tested molecules with higher polar surface areas or with good model scores for not getting into the brain, we increased our chances of finding compounds that had a significant efflux ratio. In that in vitro assay I told you about, the MDR1 MDCK assay, where we can look at the efflux that's mediated largely by PGP. And we found that following these design rules, coming up for about half of our compounds had good efflux, and we felt this could really help to try and keep them out of the brain. I should say at this point that this strategy doesn't preclude oral absorption, so high concentrations of drug in the stomach will overwhelm PGP in the gut wall, but when you reach the blood-brain barrier at much lower concentrations, then the effect of the transporter is much greater. So again, it's a strategy that's been used before and we felt could enhance the safety of our compounds. So following up, we came along with some second-generation compounds, and this is one that we're very excited about, the NDI 5581. Still in that sweet spot for lipophilicity around 3, slightly higher polar surface area here. This compound is has a significant efflux ratio. We think this is a PGP substrate, and compounds in this series, we've shown for at least one of them with this kind of profile that the CSF to free plasma ratio is pretty low. So we're really seeing significant exclusion from the brain. There'll be some drug there, but a lot lower concentrations than in our first generation. Pleasingly, in making the changes, we've also managed to optimize the properties and improve the kinetic solubility quite a bit and the thermodynamic solubility, and that always helps. We've also managed to optimize away from those off-targets we saw, so very little effect now on the dopamine transporter or the alpha-1A receptor. Because of that cyclopropyl group, we've also got rid of our glutathione trapping, and so we've removed that reactive metabolite risk. We still have really great activity, just in a mouse this time. Hamsters are incredibly aggressive metabolizers. Not all species Not all compound classes can be optimized to work in hamsters, but in mouse, where we have, again, a good model of VL, with Leishmania donovani, we can get great knockdown of the parasites at doses with exposures that we think we could match in human. Again, relatively low clearance compound with quite good oral bioavailability and a predicted human dose to match that concentration that's efficacious in the models, just 10 mg per kg BID. We think that's in the developable range, and we're optimistic that that's something our pharmaceutical development colleagues will be able to manage. Importantly, we've explored the pharmacokinetics in dose-escalating rat PK studies from 10 to 150 milligrams, and we've seen reasonably linear increases in exposure, which is, again, is really important for us thinking about going into tox and making sure that we can get the exposure that we need. So just to kind of sum up on this, we've discovered a novel series of pyrazoles. Just from that one hit a few years ago, 1,000 compounds later, we've got to the point of having a compound that looks like it could be a really good candidate. Terrific in vivo activity, as good as anything we see from the existing drugs or other things that are emerging in the field. Those first-generation compounds are very promising, but I think there are a number of flags against them, and we've been happy to optimize further and to try and reduce some of those flags. Taking compounds into development, having them fail is expensive, and we really want to avoid that. So picking the right time to take a good compound forward is important. So we've worked hard to differentiate the structure from the first generation, to address the metabolism issues, and to remove those off-target flags. And we think we've got a really good compound now in DNDi 5581. Obviously, the proof of the pudding is in the eating, so we need to complete the toxicology and see whether we've really achieved what we set out to do. But all being well, we hope we can select a candidate and take that into preclinical development very soon. A project like this is it's a very collaborative endeavor, and I want to thank the people that did the work in this project. I'm really just representing what they've done. So my colleagues at DNDi, particularly Stephanie Brayard, and then highlighted here that the team at Sandexis have done a great job doing a lot of medicinal chemistry design and helping us work through the issues on this project. The parasitology teams in Antwerp and London have been fantastic, turning around so much data for us and giving us so much help and guidance for the medicinal chemists. The team at Takeda have been wonderful. Masahiro Kamura, I can't say enough about his contributions on the design, and the rest of the team there, and Yuichiro Akawa as well, been incredibly helpful in accessing more help and resources for us from within Takeda. At the early stages of this project, the folks at Pfizer did what they could to help us. It was tough. Pfizer was going through a lot of changes, and they couldn't join us on the project, but they did what they could to help. And Alan and Sarah Skerritt, who's in the audience, and others were really kind in and helping us to get some extra data generated within Pfizer on the series. So thanks to them as well. And then the heavy lifters at WuXi that have made all of those compounds and done all the PK and so forth. So thanks to them. A long list of donors. Projects like this don't happen for free, and I can't thank them enough, particularly the GHIT fund that's really picked up the bill for the majority of the lead optimization project over the last couple of years. So thanks very much to them, and thank you for your attention. I'm going to go on. I was asked by the chairman to go on and just give some closing comments, and then if there's any questions at the end, I think. So I just, I say again how appreciative I am, DNDi is, and I know the other speakers in this session are, of being able to talk about malaria, TB, neglected diseases. So in the session this afternoon, we've heard some, I think some exciting science, some great developments, and you can see the different levels of development and sophistication against some of these diseases, but there's still a lot to be done. So if you care to take a look at the websites of the Medicines for Malaria venture or the TB Alliance, you can see exciting pipelines of compound classes, mechanisms of action, opportunities for combination for new treatments for malaria, or the complexity that we've heard about the different stages of malaria. And similarly with that, as Kelly told us, long combination treatments for TB, difficult treatments, we really need some new drugs and better combinations. So it's good to see some things marching into development. There's not so much there. Clearly, these are difficult diseases to work on. Good progress. I look forward to seeing how these work out, but clearly there's still a lot of work to be done, and translating these discoveries into new treatments is hard work. We've heard about the challenge of resistance. We've heard about parasites that hide out, that are dormant, latent TB, sleeping malaria parasites in the liver, etc. So clearly there's a lot of work to be done, but it's exciting to see what's happening. I'm just going to mention a little bit about sleeping sickness. I gave you a heads up about this earlier. When DNDi, as an example of a really neglected disease, when DNDi began working on sleeping sickness 13, 14 years ago, this was the standard of care. It hasn't got antimony, this one's got arsenic. So it's Melarsoprol. 10 to 20% of the patients receiving Melarsoprol died from the drug. The rest of them died, if they weren't treated, died from the disease. So not surprisingly, people didn't want to be diagnosed and treated. Horrible treatment, and really we needed to get rid of it. There was another drug around at the time, but for one reason or another, it just wasn't available. It wasn't being manufactured, and it didn't work well enough on its own. So DNDi and our partners worked really hard to come up with a stopgap. As we said, how can we quickly help those patients? Well, combining eflornithine and nifurtimox. Neither drug is fully efficacious on its own, but in a combination, it's effective and it doesn't kill patients the way that a Melarsoprol does. So since 2009, this has been the standard of care. It's still really difficult. You need 10 days of infusion therapy. You need about a cubic meter of equipment and sterile water to treat 2 patients. So to deliver that to remote resource-poor settings with poor infrastructure is not easy. And so it's a stopgap. It's made a big difference. The number of cases is coming down. But really, if we want to think about elimination and really getting to more patients, we need a simpler therapy, something that's better adapted. And so we're really excited about an oral treatment that we've been developing. This is a short course, single oral drug called fexnidazole. It's a nitromidazole. And we've now completed a pivotal trial for this one, a phase 2/3 trial in Africa. And we're looking forward to seeing how this one, the end game with this project is we look forward to its submission for registration with the EMA later this year. This will be groundbreaking, huge change in a drug that was horrible, toxic, drugs that are still better but difficult to administer, to a simple pill, 10 days treatment. Fantastic change in a relatively short period of time. And looking to the future, we think there might be something even better. So we have another compound, SCYX71508, now christened Acoziborole. It's an oxaborole. And we believe that as a single dose, this will be a cure for stage 1 and stage 2 sleeping sickness. And this is currently in a phase 2 clinical trial in the Democratic Republic of Congo. So watch this space, great promise, and we're really looking forward to helping more sleeping sickness patients with much, much better therapies. Sleeping sickness is one of the diseases that Kelly mentioned. I've got the longer list here, Kelly, with a few more. So we've gone from 17, as you said, up to about 20. It's good that we're working on sleeping sickness and making some progress. I'm sure there's more to be done there. There's another form of sleeping sickness I haven't told you about where we've not got the treatments yet. So we still need to do more work and keep our efforts up there. DNDi is working on a few of the diseases I told you about on this list. Most of those are at a much earlier stage, so we're not looking forward to registrations in the near future. We really need to try hard to bring a good pipeline forward and advance some of those compounds towards the later stages of development. There's lots of diseases on this list that we're not working on. Some of them other organisations are working on, but there's lots of need here, lots of suffering patients. More than 1 billion patients suffering from neglected diseases, malaria, TB and AIDS. So they're huge numbers, and we really need to do our best to help some more of them, I think. There are diseases that aren't even on this list. So, for example, I only discovered this year about hepatitis E. There are about 20 million infections a year, of which 3 to 4 million are symptomatic, and it results in about 44,000 deaths a year. The people that are symptomatic are pregnant women, and it's the poor, malnourished ones, particularly in refugee camps in Africa. And so if ever there was a patient population you'd want to help, I think this is an example of another disease where there's a need, and maybe if we apply what we've learned in other viral diseases, other types of hepatitis, to a problem like this, we could really, perhaps quite quickly, make a big difference and save some more lives. So I've shown you the portfolio. I'm sure we'll add more diseases in the future. Hopefully we'll fill in some of the boxes and add some more drugs, and we'd love your help in doing that. Kelly told you about the fatal imbalance, so I'm not going to repeat it. Just remember, more than a billion people are suffering here. And again, it's those people that are sick, but also typically poor, malnourished, living in war-torn parts of the world and really need our help. So I think to just have 1% of our efforts directed on these diseases isn't enough, and we're trying really hard to get more things going and to get more people to contribute to the battle here. I've talked about neglected diseases. I think we're starting to think now more about neglected patients and populations. So when I talked about HIV, clearly there are good treatments available for many HIV patients, but for babies and young children taking bad-tasting tablets and syrups really isn't great. The pharmacokinetics is different in that population too. So we're working really hard to develop a new formulation that's taste-masked, adapted combination for young kids and babies, so a neglected population. And then there's the HCV story, which I've touched on. It's fantastic, the work that's been done. The new treatments that are available for HCV, clearly saving lives. And it's really a remarkable effort from many corners. Unfortunately, the cost of these combination therapies is a barrier to access for the majority of the patients that need them. So yes, you hear about millions or a small number of millions of patients that have been treated and cured, and that's great. But there are hundreds of millions of patients, and they can't get access to the treatments because they're too expensive. There are deals that have been cut by the companies that have developed these combination therapies, and the prices are coming down through the licensing agreements in Brazil and India and other places. But this still isn't low enough. Even at these prices, the governments and healthcare systems cannot purchase enough drugs to treat the patients that are sick. And so our objective is really to try and come up with some treatment options where we're driving the price right down to a place where $100 or certainly a small number of hundreds of dollars where the drugs can be available to everybody that needs them. So, there's some challenges here, but I think it's important to mention neglected patients as well as neglected diseases. How can you help? Well, you've listened, which is great, so thank you. I think what we do, and I'm sure you try to do, is to keep the needs of the patients at the focus of what we do. There's many ways that researchers can support the scientific projects we're doing. It can be from having your own projects. I think we'll hear about one from GSK tomorrow, looking for a drug for Leishmaniasis. But you don't have to be fully involved. You can help in many ways. So companies that provide access to compound collections like Pfizer did for us, researchers that give advice, help us with in-kind support and so forth. Really valuable. Joining consortia, doing a little bit here and there with spare capacity really makes a big difference to some of our projects. As I mentioned, none of this is free, so we have to work really hard to raise the money to do the research and development. We don't look to sell drugs at the end to make a profit. We look to raise the money to de-risk their development such that they can be made available at no or low cost in a sustainable manner for the patients that need them. So the model's rather different, and we really depend on generous financial support from many donors. I mentioned ways that you can help, and I just couldn't finish without mentioning a few open innovation, highly collaborative models that we're really experimenting with and excited about. The first is our NTD Drug Discovery Booster. So this is a consortium set up by DNDi with now 7 global pharmaceutical companies helping us to do our hit-to-lead expansion. When we find those precious hits, and I told you how hard they are to find, we want to do everything we can to turn those into lead series and to do it in a way that's as efficient as possible. We know there are probably related compounds in the collections of pharma companies, and if we were to work with one of those, I'm sure they could give us some help. But when we work with several companies, and when we find an interesting compound, they all go and look for better analogues, and we keep iterating. We find that we're really making some interesting discoveries and learning a lot about what is and isn't in terms of the lack of overlap between corporate collections and how we can really work together as a community. And my colleague Ben Perry, who's sitting in the front row, has poster 58. He would love to see you today, this evening, to tell you a bit more about this project and show you some of the really interesting results we've made with this project. We also have an open synthesis network, so we're connecting with undergraduate researchers and PhD students around the globe who are often, as part of their training, doing chemistry projects, making things that have been made before. Aspirin, paracetamol. Wouldn't it be nice if they made a compound that hadn't been made before that was part of a bigger project? And so by working with us, we're helping them to design and synthesize compounds which will then test for them and share the data. And it's part of a bigger project. So even if an undergraduate student can only make 1 or 2 compounds in their final year project, they might be the ones that make the difference. And it's really motivating and engaging, and the students are really enjoying being part of that. We'd love to tell you more about that. And if anybody would like to participate in that, please get in touch. We'd love to have some more help. We're also doing some completely open projects. So it's very collaborative. We respect other people's IP. We're not looking to generate our own. So we can do our work in the open. I can tell you a lot about our projects very early. And we have a project where we're trying to find a new drug for mycetoma in a completely open environment with a different collaboration, a different consortium. And just a quick flag, a project we have with the Medicines for Malaria venture, we're trying to put together some pandemic response box collections of compounds which are stalled candidates or interesting classes of compounds with activity for various antiviral targets and antibacterial targets, which could be used as repurposing opportunities, lead optimization, starting points, or as tools to investigate further the biology of the parasites, of the pathogens that we may face when the next Ebola, Zika, chikungunya comes along. So these are things that I think we all have an interest in, and we welcome people's help. Thank you very much.
Right. I think we have a few minutes for a few questions.
Question about the metabolism of the development compound you had.
Yep.
So you shifted the metabolism from the aminoparasol, but you ended up with a trifluoroethyl ether. Do you see any dealkylation of that to generate TFA?
As far as I know, we've not. We see multiple sites of oxidative metabolism, but I don't think we've seen any evidence for that. It's one of a number of compounds as well, so not all. We've got some related candidates that don't carry that group, so if it turned out to be a problem, we could move away from it, but no data at the moment that suggests that's an issue.
Perhaps I can ask you a quick question. I work with the European Lead Factory, and to me it seems like a fantastic resource. Is there opportunities for you to access that as a start of high throughput screening programs?
Yeah, I think it's a really interesting point. Up until recently, we've been working in the dark with phenotypic assays, and that's not been something that's really been fitted with what European Lead Factory is about. Happily, for some of the diseases now, we're moving into an era where we're deconvoluting the mechanism of action of phenotypic series, which is telling us about mechanisms and pathways, and also there's some really good basic science going on suggesting and looking at genetic validation and other methods of validation of some targets. So I think we're now at a point where in the next few years I expect we'll have an increasing number of target-based, structure-based projects possible, and then I think using tools and partners like the European Lead Factory will be great. I think that will give us an opportunity to really try and optimize potency in a way that we've not been able to so much, and probably improve on potentially on safety as well. So.
Just here. Yeah.
Thanks, Charlie. I just had a question around whether you looked at the conformation of the pyrazole urea motif, and just whether that was set up in an intramolecular hydrogen bond and sort of bicyclic mimetics at all.
Yeah, it's a good question. We've wondered about that as well, and we actually spent quite a lot of time making a lot of 5-6, 6-5, 6-6 bicyclic systems, trying to see if we could probe that. We didn't find examples where we were able to retain the potency of the acyclic ureas. Maybe that we weren't smart enough. We still haven't tried the right thing, but we tried quite hard, and quite a lot of those systems get quite hard to make. So I think it's a question we still don't necessarily know the answer to. If we can get to the bottom of the target and start to understand a bit more, then maybe we'll be able to answer that question in the future.
Okay. Oh, there's one more there.
Maybe just related to that, have you ever tried the isothiazole? Might not be quite good for log P, but it's the sort of sulfur-oxygen contact you would have replacing the hydrogen bond with sulfur.
So replacing the pyrazole...
The NH with the sulfur, and making the isothiazole, which then sort of has the sulfur to oxygen contact in plane.
We have tried quite a number of carbonyl replacements and isosteres without too much joy. So, yeah, it's a good idea, but we've not had much luck there.
Okay, if there are no more questions, I'll draw this to a conclusion. I'd like to thank all the speakers this afternoon for a really fabulous session.